Yeah. So at the same time, because when you speak from your seat, probably it won't be able to record. So you ask your question, and I'll repeat the question so that for the recording, it will be easier for the people who watch the video later. What question was asked and what is the answer? Okay. So I'm treating this almost like a regular class, meaning that I'll try to go slowly and then make sure that you are able to follow with me, and make sure that you are able to understand the ideas, the concept that I'm presenting. And at the end of the day, you need to take away something from this lecture. So make sure to follow the lecture carefully, and then because it's interactive, you have an opportunity to clarify doubts right here. And then you need to think about, okay, what is there for me? So if I were you, the question that you need to ask is, what is there for me? What is that I'm learning? What can I do with the information that you are gaining from this lecture? So keep those perspectives in mind, keep those points in mind, and let's continue. So this topic is very dear to me. You can call that as vehicle to vehicle communications or drone to drone communications, but in the context of unmanned aircraft systems, which UAS stands for, it makes more sense to say it's a drone to drone communication than calling it in general vehicle to vehicle communications. But to begin with, the work started under the topic of vehicle to vehicle communications in the airspace. Obviously, it is different from vehicle to vehicle communications on the ground. And just an interesting fact is that vehicle to vehicle communications has been there for a long time, especially for ground vehicles, for many years. And there were radios, and there is something called DSRC. They are also associated IEEE standard as well. But somehow it didn't pick up. If it picked up, by this time you would see that your car is actually talking to the signal lights. Your car is fully autonomous, interacting with other vehicles. All those things would have been possible, but it was not it is successful, but still in the labs. People are doing a lot of research. I'm talking about the ground vehicles. Okay, vehicle to vehicle vehicles for the autos or for the cars or the trucks still didn't reach the level that we wanted to. Okay, the interesting question that came up, in some meetings, is that which one is going to happen first? Is it going to be fully autonomous car or a fully autonomous air vehicle, which is going to come first to the society? Just think about it. This is a food for thought. And the person I'm crediting this presentation is Jaya Shravani, and she was my PhD student. She recently completed her PhD student, and I asked her to help me with the presentation. Okay, so typically, I have a lab. My lab is called Autonomous Systems Lab, and in that lab we have PhD students, master students, and undergrad students. In fact, today I received a request to nominate an undergrad student, and that student actually had a couple of presentations, conference papers he presented in IEEE meetings, and then he was also he wrote a journal paper. And the most fascinating fact is that the reviewer said the paper is very pleasant to read. So there were some comments, but that is the thing that we need to look for. When you write something, if you take it seriously, if you take the job, take the task very seriously, meaning that not like seriously. What I mean is, okay, this is a nice job and you want to enjoy the job, and then if you do it right, then a lot of people will read your work. Once you publish or when you present in a conference, then a lot of people will read the work and they cite your work, and that is important for your work to see the light and make sure that other people can follow up and do something else. That is what is the value of research. So anyway, So this work started a long time back, and there are several publications, several presentations I gave on this, and probably this is a summary of what happened in my lab for over several years. There are two components to this. One is the protocol, how or why and what happens, or why do we need drone-to-drone communications, number one. And how do you accomplish this? How do you make it happen? So more specifically, in this component, we are focusing on what type of information you want to exchange and why. Okay, that's one piece. The second is what kind of technology is needed, meaning that, for example, if you are building a radio for drone-to-drone communications, then we look at the parameters like how far you want to communicate, and then and obviously the range, communication range depends on the transmit power. Plus what kind of channel model we are assuming. To predict the range, you need to know the channel model and of course path loss model, equation and all that. So there are two components. One is, so this lecture is about just the information, what information is necessary. And it is interesting to see that first of all, it is the information very intuitive. This is a research idea that started in my lab. Of course, when you start a research, you also have to look around and see who is doing what in the literature. As I said in the yesterday's class, you need to have your own ideas and calibrate with respect to the literature. So that way, you're coming up with an innovative idea that helps the technology to move forward. So in this context, we look at what information we want to exchange, and then what are the associated applications, or more specifically called use cases. So an interesting way to proceed things like this in this research is first look at use cases. Who wants this? Who will benefit? Who means what systems or what components or what what kind of devices will benefit from this. In this case, of course, we are talking about drone to drone, but go deeper and see why do you need and what kind of application, what is the purpose of this, and then think about the technology solution. Okay, so it's not sufficient. It's not enough to say, oh, I want to do something fascinating. If nobody is using this, no point. So we need to think about what are the applications and use cases, and then work towards the solution. Anyway, I think I have given enough background. Let's get into the details. So this is actually a big picture. Everything that you're going to learn or see, learn today is already depicted here. Okay? So first thing is, okay, I already gave the introduction. Somebody mentioned this term, philosophy of U2 communication. So basically, in some sense, we're talking about what is the spirit and why do you need? And I'm so glad to see that this work actually, a lot of work has happened in my lab, autonomous systems lab. There are other people working on it for sure, but we took this project seriously and then took it to so far, well beyond the current industry progress. So basically, we did a lot of work, not only in the lab, but I also I'm chairing this working group, IEEE 1920.2. As we speak, the work was completed. It took 4 years to complete the work. So what is this standard? Standard is for a communication protocol, a protocol for drone-to-drone communication. So that has started by me. Then after 4 years, we completed the draft. It is in the process of finalization, meaning there are some editorial things, that tasks that need to be done, and finally it will go to something called a ballot process. So balloting process is we put the standard out for the public, and those who are interested, those who see the value of it, those who are going to use it, they'll read it and review it and give some feedback, and then we are supposed to take care of those feedback, incorporate their suggestions or revisions, and submit again. So probably by end of this year, you are going to see that standard, even maybe earlier, by end of this year or earlier. And the one from a researcher point of view, I know some of your researchers involving in standards is very satisfying. However, it takes a lot of time. So for example, you have to attend a lot of meetings, and it's not really fun, because this kind of meeting probably you are learning something, so you're at the end of the day you have something to gain, so it's fine. But if you are attending a meeting where it takes 1 hour to decide what do we call drone, or do we call UAS or UAV, and it takes 1 hour to discuss, and maybe many more meetings, sometimes it seems like you're wasting time. It is true, it's time consuming. But in my case, something interesting happened when I was doing my PhD from 1988 to 92. Then I did some work on computer vision, low-level computer vision or image processing. That time I used something called Gabor filters. Like, the fascinating fact about Gabor filters is it is a mathematical model for some of the cells that we have in the eyes. So I was so excited about to do the work, because if you are able to model a cell in the eye using some mathematics, or you have a mathematical model, so what does it really mean? That means you can use the model and build on it to be able to explain everything that you are seeing. So that was the very strong motivation for me. For example, so think about this. If you have a model for how eyes look at things, then, and that is also not just some mathematics. It's about biologically motivated model that has been tested, that come out of the labs from neuroscience laboratories and all that. So that has that kind of significance. And when I finished my PhD, I saw that was part of MPEG 4 standard. And I said, oh, I missed this, I thought I missed the opportunity to contribute to the standards. Then I got this opportunity, and I'll tell you a little bit story to see how things work in real world. When the Malaysian aircraft crashed, I went around. Somehow it caught my attention, and I spent a lot of time thinking about why that happened, and why we couldn't avoid that. Or even something happened, why are we not knowing where the aircraft fell? It seemed to be ridiculous, and there should be something wrong. So of course, a lot of people thought about it, but no, I spent a lot of time on this. I went on my own expense, attended some meetings, and then I asked the people, pilots, it was a pilots meeting, airline pilots meeting. I asked them, well, how come you don't know? How come a pilot can't talk to another pilot, especially when you are in danger? Well, they said, surprising and interesting facts. They said, for example, when you are, those days, okay, not now, those days, they thought you have to minimize the communication. That means you need to save power or energy. And then once you are on the ocean, there is no, unless there is emergency, airplanes don't even talk to anybody. That is scary, right? That's real speaking. So, but then I said, these things are available, and there are radios available and all those technologies available. Why are not using? There are no standards, first of all, no standards. See, remember, unless it becomes a standard, it's not going to be used by industry. You can do wonderful, great work, but unless it is standardized. So that is another important, the benefit of contributing to the standards. So then I went to IEEE, then asked, do we have standards for drone to drone or plane to plane communication? Forget about drones. And they said no. They looked around, they said no. So then they said, why don't you start? That's how I got into the picture. Almost like 10 years, I spent about 10 years, and there is one standard that's already out, but it's not so significant. It's called 1920.1 aeronautical aerial communication standard. That's the reason when Dr. Sai Prakash saw that, okay, here I can give these lectures. So, and then that's how I started the work. And the second more significant work is this, drone to drone communications. So we started like a series of standards. 1920.1 is the very first, which is like an umbrella, and 20.2 is the standard that I was talking to, even though I didn't put the number, but this whole work started from there. And another important fact is, at that time they said, it's not important for the industry, but when advanced air mobility was started in 2018, the industry really needed it. Industry said, we want it now. And so as part of the process, there's an organization called RTCA, Radio Telecommunication Association for avionics or for aeronautical industry. They come up with use cases. So if you are developing standards, you also have to keep track of who are others who are interested in this, who is doing what, just like literature, So in that process, we were able to connect with RTCA, and all they did is they came up with 5 use cases, just the names. That's it. We took that as a starting point. So remember, I tell this whole thing is driven by use cases. In fact, really speaking, industry, any technologies are driven by the demand. Like for example, at the time in the beginning, like there were computers, there were devices that are like BlackBerry, but that was not, they were not so popular. But today, even though phone costs a lot, $600 or maybe $2,000, people buy it. So the demand is so high for this kind of devices. So unless there is a demand, nobody would build it. There's no point in building technology and putting a lot of money. Same thing happened with drones also. If you remember, Amazon started talking about drones long time back. So why didn't it pick up? Because we are not ready. But now, this is the time. As I told you, the drones are already delivering. Think about like burger, like pizza or salt. Even though it's not really intended for that, but if you have the technology, then why not? By the way, the point is, salt costs probably $1 or so, or maybe 50 rupees or 40 rupees. But then, do you want to send a drone which costs like maybe 3,000 rupees for delivering? It's only, these are only trials, but probably maybe if the deliveries become less expensive, this becomes a common thing. But we are not interested in this. Particularly, I am not interested in that kind of thing. What we are looking for is killer applications where things make a difference. Use of technology makes a difference between life and death, and that is like healthcare application. Okay, and then if you for reducing the pollution, for example, environment pollution, it makes sense to use air rather than ground, provided this alternative is better, not only in terms of finances or expense, but in terms of pollution. If you are able to save, or if you minimize the pollution, environmental pollution, why not? Even it costs more money, that's fine. So those are the applications we are looking at. Okay, it's nothing to do with defense, nothing to do with entertainment, but these are real world applications that make a difference to the society. That's what we are looking at. So the thing is, what is the need? When I say philosophy, this was coined by some of my friends. So need, philosophy, objectives, technologies, use case scenarios, and standards. And primarily, the drone-to-drone communication is necessary when two vehicles are so close, and we need to have a way of avoiding the accident. So as we discussed yesterday, if you see one drone, yeah, it's fun. Watch the drone, take video, and all that. But if there are hundreds of drones, it becomes nuisance, and this is called scalability problem. You have to always think about, anytime you design a system, you have to think about what happens if you scale it. If you scale to 10 times, 100 times. So imagine that if you have, let's give a small number, 100 drones flying in the city. I think everybody enjoying Warangal because it's peaceful, calm, less pollution, and somebody said pure air. Suddenly things change if you have 100 drones in the airspace. Right? Not only from an environmental perspective, but in terms of accidents. See, the key thing is everything goes well, everything is going fine, then we enjoy. But the moment one accident happens, then everything will come standstill. So, and we have seen this in Tesla cars or other autonomous vehicles. One accident will start creating doubts, or it will pause the progress. So, so collision avoidance is extremely important, but in general, it's part of the what you call traffic management. Okay? How do you manage the traffic smoothly? And one interesting fact is, on the ground you have signal lights, right? They help a lot. Otherwise, without signal lights, you won't be able to manage. So, to think of it, Can you have signal lights in the airspace? Obviously no, right? So one way to think about is use V2V communications as a substitute for signal lights. So you can see the value of it. Then I thought about this for about 2 years, and one day I woke up and said, why can't you have signal lights in the airspace? Until that time I was thinking, obviously it doesn't make sense. You can't put a mast or a pole or call it a signal light. But with my students, I filed a patent, signal lights in the airspace, but they are virtual. So what happened? This happened just last year. So see, when you think about a problem again and again, if it comes to the moment you wake up and you think about the problem until you sleep, then what happens? You will get wonderful solutions too. So here, the way we approach this signal lights in the airspace is completely virtual, and then no, you imagine that there is a four-way intersection. Then you put a signal light virtually, but it's managed from the ground. So basically, you are showing a green signal to one lane, just like the way we see on the ground, and red or yellow to the other lane. It's as simple as that. But you don't see the color. No, I mean, even the drone. How can you make the drone see the color? It doesn't. It's not that work. Doesn't work that way. But what you're saying, you're sending a message. Hey, you have a red signal from the ground control station. You're sending the drones that are in the lane that okay, you have a red signal, so don't go. So then, of course, other important aspect is you can't stop aircraft. You can't stop aircraft in the middle. So what happens is you need to send the signal very well in advance, so that if you have 2 kilometers distance between the intersection and the vehicle, on the aircraft, then the aircraft is going to reduce its speed so that it flies slowly until it gets a green light. But that's the way. It's not really that you are mimicking the ground, but the idea of that idea came. Of course, I thought about it, and then I gave it to my students. The work was done by students, and the students are also part of the patent. It was just filed about a few months ago. So there are many things that I brought up today. Is that we need to think about use case scenarios, and then build the technology, and contribute to standards, and then we will get into all those fine details very, very soon. So I'm quickly showing you, quickly discuss what exactly you're going to learn in this class today. One is, what if, how to handle close encounters when two vehicles are coming so close. And here is a free space. There is no what we call structured and unstructured airspaces. We're going to learn that. What I meant by structure is, you are again virtually creating this kind of structure. So these are called highways in the sky. You might have seen this word when you Google. You'll see that word. And in 2021, I think I gave this topic to a master student, and then in 1 year she prepared a nice article that was published in Drones magazine, and it's called Air Corridors, Concepts and Ideas and Implementation. So these are called something like lanes, air lanes and intersections, multi-layer. All these things were coined in 2021 by master student. Now, of course, I was guiding, I was telling, just like give ideas, but then they actually implemented them. She actually simulated them. And then again, all these are virtual, right? You were talking about lanes, but this lane is a virtual lane. The second thing is, what if there is no structure? There are benefits of having structured, and sometimes there is a benefit of not having also. We look at the pros and cons. In a rural area, hardly, if you only use drones for maybe agriculture or some of applications like that, there is no need to think about or plan for heavy infrastructure. I mentioned infrastructure. What is the infrastructure we are talking about? Suppose there is a corridor like this, or air lane like this. You have to provide communication support in the air for all the drones. So that is where communication support for drones becomes important. So it's not enough to have a corridor here. Suppose, let's say, oh, this is our corridor. So what we thinking is divide into cells. Like here is 2D, but here is a 3D. Divide the airspace into cells, and then put the cells like a sequence and call it like a lane. Multiple lanes create a highway system. And we also thinking about intersections. You're going to see that in this class. All these are purely imaginary, purely virtual, but very practical. Okay, this can be done. Then practically what happened so far, when we tested, when we did the demonstration, one flight from my university campus to a airport, which is about 30 miles. The corridor was what I call designed by or defined by Federal Aviation Administration. It's not easy to get, whenever you want, academic institutions can't get access to aviation organizations so easily. Like even if you want to do some research with a doctor, how available the doctor will be. A cardiologist, for example, if you're working on EKG or EEG or brain-related signals, you can't get a neuroscientist or a neurologist to come and work with us like the way we do. For some reason, we have the free time, but not doctors. Same way, if you can't just say, oh, let's talk to FAA or any federal aviation authorities. It's not possible. It's not easy. But fortunately, we were in a project, so NASA facilitated that. This project was done under the guidance of NASA, the space agency in the US. So just like ISRO here. So because of that, we were able to get access to FAA's personnel. So they defined at what height and what route we have to take. So keep that, so it's not, so that is the practical. But in theory, we can come up with our own framework. It may not be ideal, it is ideal, but it may not work in practicality. But sometime later, we can bridge the gap. See, you always have to start from somewhere. So you cannot say, oh, let me wait until somebody tells me what is a corridor. The idea here is to come up with a plan, go and be bold and present, and then people who are interested in, or maybe when the time comes, you will get an opportunity to work with the organizations such as DGCA in this case, in our case here in India. And another interesting thing is, one undergrad student studied something called circular intersection roundabout, and I was mentioning in the beginning of the lecture. He thoroughly studied this, the geometry of this, and he is finishing a journal paper which will be published very soon. Again, all this is only interest, your attitude and your aptitude to learn. There is no limit. Undergrad students, can they do research? Yes, they can do the research provided they put the time and effort and willing to learn and open-minded. Spend time every day, for a couple of hours doing the literature survey. Have a mentor like the professors here, and then interact with them, and you will be able to contribute to the research. Okay. All right. So I think you saw the big picture, and very clearly you can see why do we need V2V communications. If two vehicles are so close, if you don't, especially if they can talk. So remember, that's another factor. We talked about structured versus unstructured. Unstructured means free space. In rural areas, you have to assume free space because you can't put a lot of infrastructure. Because if you put infrastructure, it needs to return. You need to get return on the investment, right? Whereas in the urban cities, like Hyderabad or Bangalore, if you do it right, the potential is very huge. Many of us, I think, probably might have experience. It took 3 hours to go from home to airport, and I almost missed my flight once. But it's a common thing. For me, it's only 1 day, but for most of people who live in the city, like you have to spend 3 hours just to go to place. It's too much. So if you can come up with this solution, call it flying vehicle or flying cars or taxis, whatever we call. If you are able to make it happen, then it's a huge benefit. Okay? So it's called high risk, high reward. That kind of research is encouraged by agencies like UGC, and in my place it's called National Science Foundation. So people are interested in high risk, high reward kind of ideas and projects. All right. So, and the other things that that you can think of is Okay, if you create a scenario like this, like with we call that as an air cell. Each one is called an air cell. Again, this paper or this talk is about how to structure the airspace, how to create such kind of tiles or basic geometry to facilitate uh, traffic management, smooth flow of traffic at scale. We're talking about hundreds of vehicles. So imagine that it could be something like this, one vehicle in each cube by maintaining some separation of one, something like this, or it could be something like this scenario where the gap is more. So notice this, you can actually control the traffic, or you can manage the traffic, and you can dictate the rule saying, well, let's keep only one vehicle in each cell. That's one thing you can come up with. And if you think maybe that's too dangerous, so if you keep one vehicle in one cell, of course, let's assume there are 10 cells, you can keep 10 flights at the same time. But it might be too crowded, or maybe it's not good for safety, especially when it's too windy. So think about this. You are managing the traffic from the ground, and you can say if it is too windy, or maybe there is some hurricane or something, then you can say, oh, it's too dangerous, let's maintain 2 cells separation, 3 or 4. So that kind of management you can do from ground. See how beautiful it is. It is like you are coming up with something like traffic rules. And given that it's all virtual, first of all, that itself is very fascinating. And also practically, do you think it's possible to come up with these rules and implement? Yes, it is possible. We at least, for example, you can say, you can put a rule saying that there can be only one vehicle for in each cell, or you can say minimum separation has to be 2 cells. Again, cell is like cell dimensions also, because it's virtual, you can control, you can manage. You can say, for example, in our work, we gave roughly a number like 200 meters. There's no hard and fast rule here, but potentially maybe if you convince that this idea works and present it to aviation authorities, it's possible that they will utilize and come up with this concept, provide a means to implementation. But the key thing is this automated flight rules. That's the idea. At least is present in the US. It was at least in consideration by FAA. So just like the way we have those who may be familiar or may not be familiar, there's something called visual flight rules called VFRs, and in the aviation terminology they're called ISRs, instrument flight rules. Same way, the idea is we can have automated flight rules. So basically, you have a ground control station on the ground, and then we should be able to manage the whole traffic in the air and implement or enforce this kind of traffic rules. That is the big picture. But in terms of implementation, in terms of actually traffic management, you need to have a way of communication between 2 vehicles, and that's exactly what we are trying to do. But remember, there is another aspect here. What if the other vehicle doesn't talk? Then that becomes non-cooperative vehicle. So even though your vehicle you are looking at is equipped with all the sensors and radios, other vehicle may not have those radios. And another reason is, even it has a radio, something may fail. So you have to look into that scenario. So that's called cooperative and non-cooperative vehicles. So then what do you do? And obviously, something should come to your mind. I believe you need to depend on radars, right? So we need to use radar, and there are radars that you can place on the ground, and depending on the quality or performance you expect. Again, performance means how far you are looking in the airspace, how far, what's the radius of your range. Can you repeat, please? Yeah. So the question is, please sit down. The question is about how do you define, like how many drones can fly. So one idea is, first we are creating a structure in the airspace, right? And then the way in this case the way it works is, before one vehicle moves to another location, one cell to another cell, it has to make sure it is empty. Okay, so in this case everything is occupied. This is the probably worst case scenario, that if you have too many vehicles and you have to have, and everything is, the weather is good and there are no issues in terms of flying, then it is possible to have this scenario. And then each vehicle has flexibility to be within the cell. For example, if you define the cell width to be 200 meters, there is sufficient space for you to wiggle around, to move around. So before you move from one cell to another cell, of course you have to make sure the other cell is empty. The better way is to do something like this, where you give enough space and then you can again put the rule saying that this vehicle will move to the next space or next cell, provided these two are empty. So basically, if you assume smooth flow, then this is okay, that everything is moving smoothly, no issues in terms of traffic, then we are good. Okay, on the other hand, if it is too windy, then you may want to increase space. So it is okay it is safe as long as you make sure that a vehicle will only move to the next cell, provided if it becomes empty, if it is empty. So that, are you okay with that? Oh, you're talking about vertical. Yeah. So I'll answer that. So the question is about, how about multiple lanes, right? So something like this. So the issue is, we feel like there is so much space, but practically it's not. So if you look at there are some tools we can actually try. There is something called flight aware, and you can also buy a small device that is like a transponder. It's called ADS-B receiver. I think for few hundreds or maybe a couple of thousand rupees, I think we should be able to get it. So if you're looking all these messages that through your device, you will see that the airspace is not really that empty. So to have this kind of multiple layers, there should be a lot of space. Now, even though we feel there is a lot of space, but practically it's not. So those are the limits. But of course, if there is a way for us to have multiple layers, that also is a solution. But we are right now thinking about, actually in this paper we talked about both multiple layers as well as this. All right, now let's get into a little more technical details. So by the way, this is how an air taxi look like. This is from, there are many vehicles. By the way, platforms are already there. Yesterday I was giving a talk, and in some other venue, a company called Whisk. There is another company called Joby Aviation, another company called Archer, another company called Reliable Robotics. All these companies already produce the vehicles. It's not that these vehicles are not there; they are already there. So what is stopping them from actually offering the services? First of all, they need to be certified. Number one. Number two is, we don't have regulations yet. We didn't come up with enough regulations. If you let them fly, they will fly, and then you'll see a lot of accidents. So we are in the what you call at the edge of this transformative technologies becoming a reality. They are there. They're about to come, but we are not yet ready because standards are still missing, regulations are still not there, and safety things, they will be safe, but right now they're all ad hoc. So that is where we are. Okay. Yeah. 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 In fact, yeah. So that's that scenario. Yeah. Let me give some answer, and then you can come back. So the question here is that what if both vehicles are not communicating and there is no structure in the airspace? So in that case, it is the vehicle's responsibility. Suppose you are the operator. By the way, operator is the responsible for everything. Whoever is operating, the drone is responsibility of the operator. Some accident happens, people will sue us, sue the operator. So his job is at risk. So operator or the vehicle has to take care of itself. How do you do that? You need to have lots of sensors. So in the worst scenario, even if everything fails, there is no communication, you are not able to, it can happen that you're not even able to communicate with the ground. GPS is not working. So this kind of scenarios can happen. In that case, it's a responsibility of the vehicle and vehicle operator to fly safe and or maybe land on the ground as soon as possible. But in terms of situational awareness, using sensors, variety of sensors are there. Right? Cameras is one thing, but no one sensor can do the job. You need to have cameras first, and then LiDAR, radar. Onboard radars are also available. For example, if there are birds, the flock of birds, then that's an example for non-cooperative vehicles. So that's a scenario. When we talk about structure in the airspace, only in urban setting. In rural setting, we don't have to think about. It's no point in having a structure, and because with structure comes the responsibility of having infrastructure on the ground. For example, if you have a corridor like this on the ground, you need to have some very specific radio stations support communications. Number one. Number two, weather is extremely important. So what is happening in the industry is today there are something called micro weather radars. So we need to have weather stations on the ground along the corridor. So all this infrastructure is required. In fact, there's a big debate, when we were proposing this. As I said, this whole work about structured airspace started only in my lab. It's a new topic, but in a different way you can see in some other forms, there are a lot of people who work on this area, so you can see some other ideas. But this idea primarily came from my lab, and we had a discussion with another professor. So why do you need structure? Why are you imposing structure? Because that is actually delays things. You are restricting the vehicles to fly only in this road. But so that was the discussion. Okay, so should we have a structure or not? In rural areas, it doesn't make sense because you don't want to put a lot of infrastructure in the places where you don't need to fly. Like think about subway. In cities like major cities in Hyderabad or Bangalore, it makes sense to have subway stations. But what's the point in building lots of roads when nobody is going to use it? It costs a lot of money, by the way. That money is not. It's like too much money is required. Like for example, I was writing a proposal from government funding. I think it was about, I'll give the numbers, like $8 million proposal. They said, and the response was that even we give all the money we have, you won't be able to build this. And then another example is recently for DFW, and I was part of a team. Together we are figuring out what does it take to be able to have such corridors or such services in the city like DFW, and the minimum estimate is about $40 million. So it's very expensive. So you don't want to do all this work when there is no demand. And so in rural areas, this kind of scenario works. When in urban setting, this kind of things work. All right. This actually I don't want to deviate into this topic, but even scenarios like public safety also has to interact with. It's not, these two are not different. For example, if you have drone deliveries or air taxis in the city, then suppose there is a need from a public safety agency like police or law enforcement if there is a need to survey a particular location. For example, there is an accident. You want to, public safety agencies like police and firemen, fire station, they may want to send some supplies. So these two coexist. They have to coexist. So in fact, as we speak, in my area, in DFW, Dallas Fort Worth, this is happening. Public safety agencies are working together with the commercial drone delivery companies. They are coming up with standards, how to coexist, how to send a drone to an emergency scenario in the middle of drone deliveries, and then how to get priority, because when ambulance comes in, we have to give way. All the vehicles have to go to the side and give the way, right of way for the emergency vehicle. So how can you make that happen? But it's not just an idea. It is actually they're building practical means, processes, and standards to do that. A simple example is, you're going to see that later, in the messaging that we designed, you can have a field called priority. Then if the priority, say in my message to one vehicle is sending another message to other vehicle, in that message put a priority flag. My priority is 1. Then the other vehicle will realize, okay, this is some critical mission and it has to give right of way. So we talk about what do you mean by right of way in a minute. All right. These are standard things. For any drone, you will see that drones will help us to enhance situational awareness or messaging specifically, improved safety, and in general, for the applications of drones include mapping and surveying, surveillance, data collection, increased accessibility to services. Right? All these are standard. I will move forward, and this is something that you may want to take a note. Every few years, agencies like ISRO and NASA, they come up with some strategic plan. So this is a plan, strategic implementation plan in 2023. I believe 24, I don't think there is a new version of it, but potentially maybe something else will come in future. But at the time of, at this point, at present time, these are the what I call key ideas for NASA. So I think out of all this, what is relevant to our research is something called assured autonomy. So what do you mean by that? We want autonomous vehicles. We want to manage autonomously. We want to manage the airspace autonomously. We want to manage the platforms autonomously. At the same time, we have to have guarantees of safety. Obviously, it's very clear. Safety is so critical, obviously, right? There's nothing, we don't have to argue about it, or don't have no need for further discussion. Second is trust. How do you give the trust to the people? Like, if there is a autonomous flight, would you go and sit in it just for a ride? Do you think it is risky? So you have to provide that kind of trust. I think I asked this question many times, and then the answer is no. In fact, even at my home, when at dinner table I asked this question, everybody said no, unless 100 flights flew successfully, safely, then I can sit in. That was the answer. But as a researcher, and I put a lot of time in this, and I'm ready to. I take the risk. I want to fly. Potentially it is possible, because I work in this area. I'm not only hoping it will happen. When something like this happens, people might ask me, would you like to take ride? If they ask me, I'll say yes, without a doubt. But for the common person, we need to provide the trust. Then only this will be successful. Not only individual people, but as a society, we have to provide that kind of comfort. Things are better for you. Like, for example, in terms of airport safety, it takes a lot of time, right? Now, an hour, at least an hour, that more time than before. But people, we understand that it's better for us. Before you get into the flight, if the assurance that there's no guns in the with anybody, there is no crazy person in the flight, it's important for us to before we get into the flight. So it's okay to spend 1 hour. So that kind of assurance. Drones are going to create noise, but still, at the end of the day, they are going to benefit the society. So that is the key thing. The idea here is safely implement autonomy in aviation applications. Until and unless this is guaranteed, no technology like air taxis and air ambulance will not take off. Okay? At the same time, there is so much of energy and enthusiasm. The expectation is by 2030, we are going to see in some major cities, probably Hyderabad too, or in major cities in like Bangalore, Hyderabad, Delhi, potentially there is at least there is a possibility that that can happen. All right. So let's spend few minutes on what exactly is the meaning of advanced air mobility. It was started like urban air mobility, then it was changed the name to advanced air mobility. There is another name. I'll bring it up later. So today they have a different term, but generally we are referring to air taxis and air ambulances. That's the key idea. Okay, when in yesterday's class we talked about drone deliveries, but those are small drones flying about 400 feet, but these vehicles are flying about 4,000 feet, 10 times higher altitude, plus large vehicles. An example is that you saw before in the previous slide, typically helicopter size. Okay, and then even then, if you are depending only on the battery, the ride is only going to be like 20-30 minutes, not more than that. So don't expect, unless there is a fuel like gasoline or other source of energy, with battery powered, you can only fly about 20-30 minutes. But that's sufficient enough to take you to airport or some emergent to hospitals and all that. Okay? And of course, there are other benefits, search and rescue operations, quick transport to hospitals. Those are the benefits. And then other applications are there, but again, I'm not so keen on. I mean, this we don't need to talk too much about this. All right. In some of the slides, we put the source. If we pick any idea, just some suggestion for all of you is when I see students coming into my university, they lack some skills. One of them is they don't know that what is plagiarism. Just because you can't, just because you find the picture on the internet, you can't just put it in your report. The minimum thing that you need to do is give a reference that where you got it from. But this is also not enough. You're supposed to actually talk to the person who took the picture, get permissions. Let's say, for example, you have published an IEEE paper and you designed a picture, nice picture, and then you took time, spent about 2-3 hours to prepare the PowerPoint picture or some tool to come up with a diagram, and you put it on your paper, and somebody takes it and put it in their paper. Then when you find it, you find, no, what is this? I've worked so hard to do this. So it's also called plagiarism. People don't know that there is something wrong. So it is important for us to at least acknowledge where you got it from. Sure. Yeah. It is 1 hour plus 15 minutes. So if you look at the last bullet, to provide assured autonomy. Now once again, autonomy means we want the vehicle to be flying autonomously and safely, and assurance means you are guaranteeing the safety. So for that to happen, you need to have two things, or actually all the things that you see on the bullet, on the flight. First of all, we need an autonomous vehicle. That is a vehicle that can fly on its own. And there is a wonderful definition I saw on the website of WISC, I believe. If you go to WISC website and say, they define what do you mean by an autonomous vehicle. But in general, the simple idea is the vehicle that can fly on its own. That's the idea, right? Without a pilot, obviously, without a human pilot. It doesn't mean that you are removing the human being from the loop. You need a pilot, but the person is sitting on the ground, just watching over, planning things, and until the flight takes off, and until it lands, he will be observing. The person will be observing, and if something happens, we need to handle that. Okay. In this context, I did a lot of reading. I read a lot of articles in the context of human autonomy teaming, and that's the fascinating facts are nearly about 50 years ago, the idea of human autonomy teaming started, and every 10 years there is a nice report that came out from a think tank called National Academies Press. They look at the state of art and say, do we need humans in the autonomous world? So can we do away with humans in the world of autonomy? That was the question. And they actually come up with a punchline at the end, say, oh, yes or no. And every 10 years you have that kind of report. And it was not really planned, but it seems like in 50 years, since that idea of human autonomy teaming has started, 50 years will happen around 2028. So my first paper that I read was, go ahead. In fact, the definition itself, people define in many ways. That's what I was telling before. In some of the standards, defining autonomy takes few meetings. So there is a autonomous vehicle, autonomy versus autonomous. These are a lot of words. But the thing is, autonomy refers to generally, in our context, okay, your vehicle is flying on its own with no interaction from the human being. Ideally, that's ideal. So as I said, 50 years back, nearly 50 years. That actually, to be specific, it was, I think it was 78 to 2028 is about 50 years, right? So first paper or first report from the National Academy Press, which is like a think tank in the US, they gave some suggestions, ideas about. Okay. And even in 2018, the last report was in 2018, and the report says we cannot take out human being from the autonomy loop. Okay, that's number one. But even now, by 2028, the reason I found it interesting is 50 years later, which is in 2028, FAA is planning to have fully automated vehicle. But it still doesn't mean that you take out the human being. Human pilot has to be watching over, and sometimes in casual discussions, I was brought up some incidents. Like for example, in one scenario, the pilot landed the aircraft with full of passengers in a river. So imagine those kind of scenarios where there is something is sudden development in the airspace. How does the remote pilot or human pilot have to react? So in the case of human pilot with vast experience, he decided to land on the water and it was successful. He saved people. What happens if it is completely autonomous vehicle? Will it do it on its own, land on the water? Probably, we don't know. But at the same time, I thought human is better in those cases, right? Which is because, a human being, a human pilot can get into unexpected scenarios and still take a good decision. But what would happen with an autonomous vehicle? If you do not know, if you don't have the history of such incidents, then will an autonomous system come up with a good decision to handle the complex situation? So that is questionable. But some people believe, which makes sense. Many times, it is a autonomous system or a machine can make can take a decision, better decision, and in general, for example, if you look at the history of aviation accidents, most of the errors or most of the accidents happen because of human error. So what do you say? So this question of the role of human being in the autonomous systems is still an ongoing debate, and it's not about technology. The answers come from psychologists, behavioral analysis, those kind of areas. So it's not engineers who will decide, okay, just because we have a great things like AI, artificial intelligence and all that. In fact, I chose not to use the word artificial intelligence for now. The point is, if there is a historical evidence, historical knowledge, you can feed it to the machine, and then probably using that knowledge, the machine can take a decision. But if you are in a totally unexpected scenario, how would the system behave? That is questionable. So human is better. Definitely, you can argue either way. But I mean, personally, I feel it is a human who will make a better decision. Anyway, so but in terms of coming back to our autonomy, there are two things: autonomous vehicle and autonomous airspace management. Both are critical. In fact, if you look at the report I was talking about, by the way, all these reports are available and publicly. So you can, if you are interested in one topic, just do as much search as possible. And because of Google and Google Scholar, and you have all this information readily available. It's a question mark because the official report that I read in 1998, I mean, again, remember, the reports come every 10 years. I saw one in 1998, I think I saw in 2008, and I read a report in 2018. These are coming from think tank called National Academies Press, where they invite experts, subject matter experts, to discuss and come up with a report. Like, for example, even for autonomous advanced air mobility, there was a beautiful report that came. What areas we have to pursue? Same thing with AI also. What is the state of AI today? Those questions, I think it's better to go with the report and understand the spirit of what everybody thinks. As a group, as a research community, what are the answers to some of the questions? I think we have to refer to those reports. So, in that context, yes, the answer is human is required. I don't think in 2028 things would change dramatically. So another important direction is the report, the plan by Federal Aviation Organization, Federal Aviation Authority, Administration, FAA, that said, let's go slowly, crawl, walk, run approach, and then let's have a human pilot in the beginning, and slowly move towards without pilot. So it means that in the next few years, there will be a pilot, even though it's an autonomous vehicle, there will be a pilot on board. And then, right, yeah. That's true. So just for repeating your question, in a challenging environment like in India, challenges are everywhere, but it's more challenging for us because of population and density and what you call space limitations. So it is more challenging here. And you're right. I believe Tesla recently announced they're going to start their plants in India. Yeah, of course, even with all those autonomous software and autonomous vehicles, it is difficult to implement that self-driving cars or have launch self-driving cars in India. But space is, I think, it's at least it's easier, right? It's much easier to manage. So that's a plus point for autonomous vehicles. So keep this thing. Both are important, and then you need to have standards and regulations, and the high importance to be given to safety and security. And this is not the least. Community acceptance is extremely important. If the in most of the cases, they actually we ask the community to vote. If the community doesn't want autonomous vehicles, then you cannot do anything. Hmm. 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 Right. Hmm. Hmm. Right. Very interesting there. So that I think it's a very interesting dynamics, especially in India. It was successful. Digitization was very successful. Yeah, we cannot predict. Yeah, it can happen. It can happen. Right. Yeah. See, one issue is they use only cameras. They don't use other sensors. So that's a little bit of challenging. Follow. So here is what I really meant by airspace management. So we need to manage the airspace efficiently, and normally the airspace is completely regulated first of all, and then it is managed by aviation administration. But here we are looking at a technology solution. Okay, so and all these are basically some ideas only. None of these are practical at this point. So the term structured airspace means you are designating some space and creating this kind of lanes or routes or pathways or tracks. And for a long time we used the term air corridors, but then it was again a pushback by some agencies. Don't use air corridors, call it something else. But I think it makes sense to use this in our context. So the difference between structured and unstructured is you don't have this kind of airspace management in case of unstructured. There is no specific route or anything. Like I think the analogy is if you have roads, it's easier to go and travel on roads, especially you have a truck or a vehicle. So if there is no road, you don't have an option. And then efficiency is, if there is a designated route, it makes sense to follow that route. But then the question comes, why are we restricting to only this route? Suppose I say, oh, you are only supposed to fly only in this path. What about this space? So that's the restriction. So some people feel that why are we restricting this? But it is a good reason for restricting because, as I said, you need to build infrastructure on the ground. If you say, okay, this is my route, then below that route you have to provide the infrastructure for communication plus weather sensing. At least these two are critical. So you can't put a lot of resources everywhere in the city. So and then again, the good example is, suppose I'll use, because of this leisure, I want to use something far from you. So basically, if I say this is my route, then below the route you are supposed to provide the infrastructure. So there is no point in creating such infrastructure in rural areas where you don't have a lot of traffic. But if there is heavy traffic, you better have this infrastructure. Okay, that gives you what you call proper way to handle the traffic. Basically, it's like a traffic management strategy. So that's what I meant by structured and unstructured. That will help us to manage the airspace autonomously. As I said, the two things are important: autonomous vehicle, autonomous airspace management. And if you look at the again some documents, you will realize that you will see that vehicles are of different sizes, and then commercial aircrafts fly about 30,000 to 40,000 feet. Then small drones fly about 400 feet, and then helicopters are somewhere in between. There are all these are well defined, and I'm not, my point here is the discussion here is not about giving you the numbers, but I want to explain the concepts. And then corridors are defined as at a height about 4,000 feet. Remember, divide by 3 roughly, that will give you in terms of meters, like 120, 130 meters. So that's the idea. And in terms of traffic management, of course you have to have smooth traffic, but the more importantly, you need to avoid conflicts. Meaning conflicts are potentially, if there is a conflict, there is a collision. Basically, collision avoidance is a key factor in designing airspace management to manage the airspace. So autonomous vehicles are fine. Vehicles can fly autonomously. That's very good. But still, you have to make sure that come up with strategies or protocols or solutions for conflict management. Okay. So here conflict means if you don't avoid the conflict, then you get into accident. So there are 3 different types of conflicts. The deconfliction means you're trying to come up with a strategy for avoiding the conflict or address the conflict or avoid the collision. So something called strategic deconfliction, tactical deconfliction, and there is another term people use, operational deconfliction. There are 3 actually. Okay. The idea of strategic deconfliction is you plan it ahead. Before the flight takes off, you plan it ahead. Like for example, if there are 10 flights already in the airspace and you are sending a 11th flight, and make sure that this 11th, the path doesn't conflict with the 10 routes that are already in 10 flights that are already there. So in terms of, think in terms of programming. Suppose you are the programmer, you are coming up with a flight route. So what you are trying to do is, in terms of space and time, it's not just the space, but you also consider time. For example, I'll use this tiles to just give an idea. Suppose there is a flight that takes off from here and then goes on along this path and it lands. By the way, vertical takeoff and landing or eVTOLs actually do that. You start from something like a vertiport, like a roof, like a high altitude, some sort of a building. By the way, we call that as a vertiport. And so basically you're saying you take off vertically and then change the direction and go horizontally and then land. So let's call the center point of each cell as something called waypoint. Waypoint is basically XYZ information. Maybe I can use this too. So let's say all these points on the way, you're taking off vertically and then flying along the corridor, like this is one of the corridors, and you land. So the points that you are flying or points that you are supposed to go through, those are called waypoints. So a waypoint is XYZ location plus expected time of arrival also included. So time is part of that path. It's not just XYZ location, but you're also adding the time of arrival. So which means that I'll go back to this. Let's say you are supposed to be here at the first minute and second minute and third minute. Then after that, let's say suppose you start at 10 o'clock. 10:01 you are here, 10:02 you are here, 10:03 you are here. So when the one flight is at this location, these two are free. So basically you are designing the path using the time and space, because okay, that's one way. If you don't do that, what happens? The other way is, okay, from 10 o'clock to 10:15, I'm reserving the whole space, and nobody can come into this. So that's one option. One option is you're reserving the whole space for the duration of the flight. We remember these durations are like 20-30 minutes, not really long. So it's all right to begin with. But if you want to increase the number of vehicles, then you can't leave it like that. You can't say if 10:01 the vehicle is here, 10:03 the vehicle is in the third slot, third cell, then at 10:03 some other vehicle can start. Right? So this is a simple logic, nothing complicated. So when you say conflict avoidance or deconfliction, what you're trying to do is you're designing the routes or designing the flight plans in such a way that a new flight plan doesn't conflict with the earlier flight plan. That's straightforward. But then what happens is, in the air, anything could happen. Like suddenly there is a high wind, or maybe in some places maybe there is rain. So if the wind is high, wind is more than like 15, maybe 20-30 kilometers, it's not, you cannot fly drones. So it depends. Of course, it depends on the capacity or capability of the flight. But small vehicles cannot fly even in 15-20 miles kilometers per hour. So it's also possible that there may be some turbulence. I think you think like the whole airspace is clear and calm, but suddenly the pilot says, "Oh, there is a turbulence." Where is it coming from? We don't know. So right. So they say, "Oh, it's turbulence," and all of us who have flown, you see, all of us have seen those kind of scenarios where, oh, you can't go to bathroom or you have to sit there and for 20 minutes or so. So the point is, things can happen dynamically, not unexpectedly. So in that case, this is about the idea of tactical deconfliction. So during the flight, you have to manage the find out if there are conflicts related to weather. When I say something like an obstacle, okay, not more, I think obstacle is better, or weather development, or there may be, somebody talked about there might be a flock of birds. So we need to predict those situations, and once you are in that situation, we have to figure out a way to change the route accordingly. So this is called tactical deconfliction. And operational is totally unplanned. Something happened and suddenly you were sent a message, you need to change the route. So route managing or rerouting, that's a very, very important aspect of traffic management. So how do you do that? One is, first of all, remember, it's the operator's responsibility. There is a person who is responsible for each flight. Okay, so that person has to first of all be informed, or he has to make the decision. And then if it is an autonomous flight, no pilot on board, so you are going to send that message to the drone. And then what happens? The unmanned aircraft will have, first of all, it is navigating through autopilot. Autopilot, some of you may have seen this small device, Pixhawk, probably, it's so powerful, it's so small device, but it can fly. So you need to provide the route information to the autopilot, and then things will be fine. But you need to define the routes. You have to design the new route, make sure that it doesn't conflict with anything else, right? Check the route for all the other constraints. Like, for example, it's not enough you use a Dijkstra algorithm and change the route, but you need to find what are the, whenever you come up with a route, you have to also check how is the weather going to be in the new route, and then is it within the limits. For example, aviation authorities will tell you can fly from in between these altitudes, so you can't suddenly change, oh, all this is free, so let's go this. That's not possible. So you have to still be within the bounds. If you want to get a little more ideas about how actually things happen, how you plan a route, and how do you reroute, there's an article that I published in 2023. I call it digital twin for airspace management. And I called it a digital twin. The reason is, So airspace management, first of all, we're looking at airspace management. And then how do you see this as a digital twin? So what I meant by that is, typically digital twin is used for cars or or airplanes. So you can say digital twin for an airplane. But what I really wanted to say, convey the idea of a digital twin for the airspace. So basically what I meant is, in the control room, something like air traffic control room, we want to see the entire airspace on your screen and on your computer virtually, so that everything and anything that is happening in the airspace, we need to have an idea. We need to see that. Yeah. Mm. 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 Yes, in fact, it is like, there is a service called DSS, Directory Synchronization and Service. So what in the context of drones, okay? Because nicely everything is planned so well, and there are also standards. There is something called ASTM, an organization that is working towards developing the standards for information sharing. So there is a service. All these are by the software services, and the beauty is, you can launch your service from your home, from your garage, like whether it's a traffic management. In fact, on my own, I asked my students, some of my friends actually, to start a spin-off a company. I called it as a data exchange hub. Collect all the data about the entire ecosystem about advanced air mobility, and then see the data, understand the trends, and focus on safety, and come up with what you call some machine learning type of solutions to manage the traffic better. So the point is, all these services can be designed by individuals like you and me. For example, traffic management. Other is weather service. Of course, weather service, you cannot come up with the weather data on your own. You need to have all this hardware, sensors deployed in the city, and then you collect the data and try to model the weather and predict what exactly happens at this height. That's extremely challenging, right? So whatever measurements you have on the ground, you cannot use them to predict at that height. We're talking about 400 feet or 4,000 feet. So one idea is, again, the people are pursuing this. They're still in early stages. Put a sensor on the drone itself. Every drone will carry a weather sensor, and look at this, the capability. You are getting the weather data at that location, specific location, to the ground, and you put all the data together, aggregate, and come up with a model to predict weather at any given time. It's possible, but for that to happen, you need to have lots of drones in their space. So all these are evolving. Everything is evolving, and it's like an ecosystem. One service depends on the other. Now, for example, if you want to come up with a rerouting, we need to figure out what is the extent of or volume of airspace that you want to avoid. How do you know that? Suppose there is a turbulence, how do you know how much area that you have to avoid, how much volume you have to avoid? There is no solution yet. And the things that we have, like global weather solutions that we have from what you call from airports, or the weather radar that we have, they are not sufficient. We are looking for exactly what is the weather at this altitude. So since I've been working with this so closely, recently, about a year ago, there was an announcement from FAA asking for, there's a challenge, a competition that was called FAA Data Challenge. And some of my students, what they did is, they tried to get some weather data from internet, from some publicly available sources, and the data set they got was from there is a place where these sensors are placed on floating platforms. They call buoys, I think. So there are sensors that are floating in some river. So they use that data for predicting for modeling the weather. and they were selected in the first phase, and they submitted the solution, and they were selected through first phase. Now we are going to, as a team, we are going right after this this trip on March 18th. We are going to, my students and myself, 2 faculty and 2 students, we are going to DC to project, and there's a second level of the competition. The point is, the weather data that we collected is from the ground. That doesn't, it's not sufficient to predict to model weather at this height. So we need better solutions. So which means that you need local weather, local and weather exactly at this height. So that one solution is again to put the sensors on each of the drone, collect the data, and come up with a model to predict weather at a specific time in a specific location. It's a very challenging thing. It's not you can imagine what kind of complexities you can see. Go ahead. It's very global, it's global weather, and you need almost like a 3-dimensional weather. The weather that you report that you see today, they are good, but we are talking, the precision is not not sufficient. Yeah, weather balloon is an option, but notice if you think about that, you can also see the weaknesses of that, right? You can have, suppose you put weather balloons. That's a good point actually. There are weather balloons. I believe there's a company called, the companies which are working in this field, there's a company called True Weather. It's a very startup company. You can look TRU. There is no E. TRU Weather. True Weather. Very startup, is a basic small company that with only few people. I believe they are doing something like that. They send balloons in the morning and then plan for the day. They can predict, they can model the weather for that day. But we need even more precise local weather. But think about this. I think I was mentioning before, in commercial flights, we see the turbulence, right? We hear from the pilot. Those kind of turbulence can happen at any time. So if you plan a flight 30 minutes, let's say 10 o'clock, and then you say everything is fine, you send the flight, but at 10:20 something can happen. Yeah. So the good is again the question is how do you reroute? Rerouting in structured and unstructured spaces. So in either case, first thing is responsibility rests with the operator, and then whoever makes the reroute, operator has to confirm that or verify that this new route doesn't have any other issues. Other issues means, yeah, you have to make sure that it's following the guidelines, right? In terms of in either case, actually, I think the answer is pretty much the same. That you make sure that you plan the reroute first of all, avoiding the conflict area, and then make sure that we are still following the bounds of the airspace that we are supposed to fly. And then even in a structured space, structured airspaces like the one we talked about, it's possible that temporarily you may go beyond the route, right? So that means, right, yeah. Yeah. Yeah, it's possible that, in fact, I have another illustration to explain that. But basically, yeah, you have to find the reroute, new route, and confirm that new route doesn't have any issues related to regulatory aspects or weather and other issues. Then only you can take. So in case of structured airspace, probably suddenly you have to open up a new route, emergency route. So another probably something related is, if it is only one time, it's fine. You can just go around and then and continue. But if it is like there is a congestion somewhere, just like on the roads, so in that case you have to have you have to have a new route opened up, and that has to be again managed by the ground control station. All right. So we learned about the conflicts, three types of conflicts. All right. So for all this to happen, yeah. Linear routing algorithm, yeah. No, but I think it is true, but for now we are assuming everything is like straight lines, right? That's practically it is not possible. Like straight line, because it's an academic exercise for now, But practically, it is not like that. Air corridors are not going to be like nice lines, yeah. It could be any shape, right? That depend. I learned that. Second, not really. The thing is, they may be like curved route. Yeah, it's like it may be curved, it may not be like piecewise linear probably. And then the what you call the altitudes at which we can fly, it depends on a lot of factors. One is population, and then second criteria is being away from airports. So those are the factors. For example, go along but the corridor itself, right, yeah, but yeah, right, that's true. That much is true. Yeah, like for example, I think the picture that we are depicting, so corridors are defined. This term is, by the way, from FAA. This picture is coming from the concepts of urban air mobility. This is not from a .com, actually, it's from FAA. So you can see this picture in a FAA document, and that the document is about concept of operations for urban air mobility. This is version 1.0. So what FAA says is that you need to fly within these heights, number one. But then depending on your location or region, the heights of the buildings, terrain, structure, and airport locations, these corridor might have a different shape. And even altitude also might be different. What works for Bombay may not work for Hyderabad or Bangalore. So it depends on the geography and terrain. That's for sure. So you will see probably some sort of a zigzag path. But for sure, as you said, flights have to be flying within the corridors, within the designated spaces. But even then, we can't forget that no matter what area you define, how well you define the corridors, you cannot avoid cross traffic. You cannot assume that, oh, from here to here it's all empty. No, it's not good. You're going to see helicopters, or you're going to see other vehicles. There is no way or no place that you can expect nice empty space. That's not possible. So corridors are not completely designated. Somewhere you can see, for example, an aircraft is taking off while the drones are flying. So those are, it is given that, and it's understood that we need to handle those kind of scenarios. Okay, now with all the things that we discussed, it's very important that we need to have communication support. Without communication support, we cannot manage the traffic. So notice that with the commercial flights, we don't have to know the location of the flight every second. But for drones, you have to know at least once a second, even more frequently. We need to track the vehicle continuously. What is the appropriate frequency, we don't know yet, but at least once a second. Again, I'm saying these numbers based on my own experience. I worked in remote ID standardization at the end of the standardization process, where I worked with companies like Intel, who are part of the team, to look at practically what are the practical aspects of remote ID standardization. So remember, what is remote ID standardization? Every drone must have a remote ID, a device that tells its location at least once a second. Okay, and the work specifically I'm dealing with at that time was what is the communication range, and I did that work with the group of people at that time. but also for advanced air mobility, I'm also looking at the trying to answer the same question. And then what's interesting is remote ID is typically for small drones, and they were expecting about 2 kilometers range. Okay, so what it means is when a drone is flying, you should be able to transmit its location information to whoever is interested in knowing the location information within the 2 kilometer radius. In fact, more specifically, it's for law enforcement agencies. The drone is flying, the guy will have a phone, law enforcement officer will have a phone, and he or she has to know, is this a legitimate flight or not? Okay, and then we don't have to think about what happens if it is illegitimate, and that's beyond engineering. But the key thing is, so we should be able to do that, transmit the image up to until at least 2 kilometers. So what kind of technologies will help? What kind of radios will help? Will Wi-Fi fits in? But interestingly, they were assuming at that time Wi-Fi or Bluetooth. Okay, it is possible if there is in the assuming it free airspace, it's possible to transmit a Wi-Fi signal to a longer distance. But for you, we know that on the ground, your Wi-Fi signal won't even go more than 50 feet. So, but in the free space, it is possible. Okay, and of course, you can always adjust the transmit power. But Wi-Fi standards come with the requirements of what can be the limit for the transmit power as well. But for the remote ID standardization, they assume that you can go up to 2 kilometers. Now fast forward, go towards advanced air mobility, large vehicle, air taxi kind of platforms. How far we want to see? How far we want the signal to transmit? Probably much more than 2 kilometers, definitely. It could be 10 kilometers or 10 miles. So, but we don't have a clear-cut standard yet. On the other hand, we got a funding through SBIR from NASA to study vehicle-to-vehicle communications. And in that process, when I talked to the program manager, he suggested a nice idea. He said, Kamish, let's not fix the range. Give me some model where if I want to go for 2 kilometers, what do I need to do? If I want my communication range to be 10 kilometers, how should I tune my system? And that was very fascinating. What I did is I gave the problem to my student, and that student is very talented, and that guy actually came up with a nice paper. I'll bring that up later. So we are building a model where how do you tune the system or vehicle-to-vehicle radio system to be able to transmit up to 2 kilometers or 10 kilometers or 20 kilometers. Okay? One thing is, like, if there is what you call, if somebody wants you to do it, then if they are giving money, this is one thing. Items, okay, yeah. So there are, of course, there are challenges. Yeah. Right. Yeah. So we are right now. We're looking at the unlicensed bands like 5 gigahertz and 2.4. Those are even the radios that I mentioned yesterday, Silvus radios that I said, with 10 watt power, you can go up to 10 miles. That was we practically did that, and it was fascinating to see, to see that. Now, what happened at that time? Not allowed, not really, because it's not allowed. But in that time, sometimes I think, if you do it for a long time and many times, then you need to get permissions. Right, you have to talk to FCC before we do any such experimentation. So with that 10 mile range, we were able to put about 4 or 5 radios in the 30 mile corridor, and we were able to create a network. It didn't work perfectly, but it was at least the proof of concept was there. It means without having without having cell tower or satellite connection, you can just use mesh networking radios along the corridor. So you can put the radios. Depending on the communication range, you can decide how many radios you need. So for 30 miles, we used one radio in the beginning and one radio at the end, and in between 2 more. So we created a real true mesh network. And in terms of performance, it didn't perform exactly as we needed because we missed. Yeah, before I get into that, so why do we decided that we need proper communication support. That's for given. And whether you get it through satellite or mesh networking radio or cellular network, it is immaterial, but we need for sure. And what is our no? So which solution you want to go? One, I talked about mesh networking, one solution. In some sense, this may be suitable in situations where you don't have cell towers. Obviously, that's a good idea. But if you have cell towers, then again the question comes: how many base stations you need? And to do that, you look at this problem. In fact, I already also have another paper. We've been working for 2 years. It's not yet finalized. Is that think about a corridor like this, and then for about whatever distance, like let's say 30 miles. I'm using 30 miles because anywhere to anywhere is 30 miles in place where I live. So it's a big city. The moment you want to go, for example, to go to school, I have to drive 30 miles. so that's the reason 30 comes into my mind all the time. But suppose this length is 30 miles, then how many base stations? When I talk about base station, I mean cell towers. How many cell towers do you need? That analysis can be done through something called link budget analysis. I believe Dr. Sai Prakash is going to make you work on a lab. So link budget analysis will give us an idea about what transmit power you need, and how much communication range you can get, and what will be the quality of the signal at the receiver. So here our receivers are drones. So that's the reason I said you can view drone as a phone, just for now, in terms of cellular service. So you put cell towers, and then if you go deeper, right now, if you depend on an existing cell tower, they're not designed to support drones. They're designed to support users on the ground. So one thing is, maybe the service provider might take advantage of this opportunity, and the service provider may place some antennas to look up. That's possible. But then coexistence of both users, supporting both users and as well as the drones, it's very challenging. It's not that easy. Or for now, there are alternatives. There's a company called ARA. If you look at AURA networks, they come up with this kind of base stations, and they are operating at 433 megahertz. Totally different network. Okay, 430. They have license for that throughout the nation, and it's interesting to look at their website, AURA networks. I worked with them for a while. They were part of our group, but later they left. So that company is placing these radio stations like mini cell towers, operating at 433 megahertz and providing communication support to this vehicle. That number of, right? That's true, because you can go for long range. That's a good point, right? But then in terms of data rate, very small, and you can, right? Have you seen there are other radios called LoRa? Many people might have, but if you look at their performance, they are not that great. They're good for like long distance and all that. So in terms of this ARA network at that low frequency or 433 megahertz frequency, it is good for command and control messages. Remember, yesterday we talked about command and control messages are small. You don't need to send millions of bytes. They're like 1 kilobyte or 2 kilobyte. That's the advantage. So you can use it for non-payload communication. Remember the term payload and non-payload. Payload communication means you're talking about sensor data, like camera data and all that. But non-payload means command and control. Basically for navigation purposes. The messages are small, like 1 kilobyte or maybe 2 kilobyte. So when we were working with them, we asked them, can you help us can you communicate routes, like we just talked about routing, right? Reroute. Suppose you want to have a new route in the middle of the flight, can you send? They said with some modifications they were willing to send vertical longer, but longer means not like millions of bytes again. 1 or 2 kilobytes is doable. Okay, that's one thing. Can you think of what else we need communication for? We talked about telemetry. Telemetry is coming from the drones to the ground. So we are talking about command and control from the ground to the drones. From the drones, we need the telemetry. So these are the minimum thing that we need. So in terms of telemetry, once again, we will go into more details in the next few slides, but primarily you are looking at location information, which direction they are heading, what is the current speed, those kind of details. See, one more thing that it is not really explicitly mentioned is that we are assuming that when you create a network, every drone has an IP address, just like a phone. So we are also, it's assumed that when you talk about network, every drone is like a phone, it has an IP address. So as long as, if you start from there with that assumption, it's clearly, it's just a network with every node can talk to any other node, and you can use multi-hop, all that will get into. So remote ID, when I mentioned remote ID, I talked about remote ID will have, it's like a broadcasting the location information, but it also has IP address too. You are actually sharing the IP address to neighbors. That brings up security aspects, right? So you can imagine we are still in the beginning. No matter how much advances we made, we're still in the beginning of the overall progress. For example, right now all this information is open, even for commercial flights. The information about location and even ID, the ID of the vehicle type, vehicle name, all these are publicly available. So how much security we need still in debate. There are some solutions. There are working groups that are working on standards, security standards. And again, if somebody is interested, please talk to me offline, and then I can share more information. Now, for example, remember there was some college student who was monitoring the air vehicles of Elon Musk and even President Trump. So all those things are there, right? So security is an issue. Like if you don't want to know where is the president's aircraft, then we have to worry. We have to think about alternative strategies. But as of now, this data is open. Okay, anyway, without deviating too much, here are I think we spent a lot of time on this, talking about the need for V2V communications and all that. So in terms of communications, there are all the options. Like we will look at some of them. One of the key thing is something called ADSB, Automatic Dependent Surveillance Broadcast. Read about this. It's very lot of information. So this is also like a transponder. It's not exactly two-way communication. So why I'm bringing the two-way communication is for negotiations of collision avoidance, you need a two-way communication. So ADSB is good for knowing where the vehicles are there, just like remote ID. And you can also inquire, you can ask a question and you can respond, you can get a response. There's something called ADSB in and ADSB out. So without going into too many details, think of it's like a transponder. You can mimic a two-way communication, but it's not exactly suitable for two-way communication. And there is something called controller pilot data link communication. There are others too, but we only highlighting few of those things. Okay, and if you go into details, you can see C-band, S-band, which are typically used for aviation purposes. Okay. So here, let's look into ADSB. And the point that we are trying to make is, whatever strategies we have, whatever solutions we have today, as of today for commercial aircraft, are not enough. There is a need for direct V2V communication, radios and hardware as well as protocols. Okay, that's what we are trying to emphasize. So for example, this is about ADSB. It's used to send data such as location information and velocity or speed to ground station or other aircraft. So ADS-B broadcast information. So ADS-B out is mandatory for most of the vehicles. So ADS-B out will tell you, if you receive a message from ADS-B, you know that where are the other aircraft nearby. That part is very clear. And then it helps us to increase the situational awareness, which in turn will help us to reduce the congestion. Because once you know that the information about your neighboring vehicles, then you try to stay away or maintain the distance. It is necessary, it's mandatory that ADS-B out should be equipped with all aircraft. Whether you want that, whether you receive the data or not, you must share your location information with others. See, it's interesting to see, if you want to protect whether you protect your vehicle or not, other vehicles want to be protected. So given that, you are telling ADS-B out is mandatory, but ADS-B is good for protecting the own vehicle. It's not? Yeah, that's why security is like, yeah. So for avoiding collision, we need to have ADS bound. ADS in is important too. It refers to system in which aircraft receives the broadcast information. If you don't have ADS-B in, then you cannot protect your own vehicle. All right. So remember, you are also sharing the aircraft number. So that's why there's a reason I'm bringing up the what you call security aspect. And I believe this is coming from, for every picture, if you see something, then that means you are giving the credit to this. So the focus of my work or my lab is primarily on the aircraft to aircraft. So when you say vehicle to vehicle, we are referring to actually aircraft to aircraft communication. So there is a need for having a designated radio, specific radio on each of the platforms to facilitate this aircraft to aircraft communication. Yeah. So if you want to little more details, the frequency band is about 1090 megahertz. So that's more like think of like a carrier frequency, but specific bands are very small, like 5 megahertz or so. And one for in and one for out. And it's like each way you need to designate the bandwidth. And these are the limitations because we're saying security is not there. And yeah, one more thing is the reason we are looking at limitations is because we are justifying, or we are trying to see, can ADS-B be used? Is it sufficient for doing what we need for collision avoidance? Okay, it is, in principle it is useful, but not enough. So for example, in those messages of ADS-B in and out, you do not know what is the context. You just know the location, but you don't have any more information. For example, intent is very important in V2V communication. What do you mean by intent? What is the intent of the mission? For example, are you flying because of emergency? How much priority you need? And what is the overall mission? What is the goal? Those things are helpful, and they are needed actually for tactical collision avoidance or deconfliction that we talked about before. So it doesn't provide any more information other than location and speed and those kind of high level information. But sometimes for V2V or for air to air communication, aircraft to aircraft communication, we need more than that. So in general, point is we are saying ADS-B is not enough. That's a big picture. So again. Right. Oh, the time for ADS-B. I don't have exact numbers, but it is reasonable. ADS-B latency in terms of processing is reasonable, but in a very critical scenarios, probably it is not enough. So I think all these are like you can assume the packets are very small, and so you can receive the message in very quickly and sufficient enough to avoid collisions. But you cannot do more what you call negotiations. See, you can't negotiate. Like for example, you're going to see some of the use cases will include for collision avoidance right of way. Like you are at an intersection, and who should get a right of way. So those kind of negotiation require more than the basic information you have in ADSB. So that's the issue. It's not about maybe we'll even in V2V you experience the same amount of latency, but the precision is not that by having a V2V you're not going to increase the precision. Right. Can you repeat? Right. Yeah. You need to. That's true. That's true. Yeah, you need to maintain sufficient distance for safety. That depends on how much time it takes for you process. Yeah. In fact, that reminds me in a scenario where I long time back I had a small grant from NASA. It's called colonizing Mars. That was the project. So I was looking some at numbers. Let's say like there is a crater, let's say, and then rover is here. For the rover to communicate, send a message to rover, it takes maybe like 10 seconds. If it is on Mars, it takes 10 seconds to send a message. So if you send a message now that okay, there is a crater, don't go in that direction. Within 10 seconds, by the time you send the message, it's already gone there. We are in trouble, right? So those are the things that we have to consider to define what should be the minimum separation. Right, yeah. Right, that's what it meant. For the fire truck, I thought something like 3,000 feet, maintain 3,000 feet. So those are because they have a big ladder that goes up to several feet, I think. But anyway, you see the point, right? You see that the need for communication and more importantly, trusted, reliable, resilient communications is necessary. To transmit, you need to have ADSB in, ADSB out for transmitting, and ADSB in is for receiving. Yeah, actually the intention here is that imagine that there are, let's say 100 vehicles, right? So 100 vehicles transmitting at the same frequency. That is the congestion we're talking about. So it is like it's not about people on the ground. Suppose say, oh, let's use ADSB for drones, okay, or for air taxis. If that is the intention, what we are saying is the more vehicles they are present in the airspace, the more congestion will happen. So which means that let's like in a Wi-Fi. Let's say you set up a Wi-Fi access point. The more users, then you won't get a good signal. I mean, you won't be able to do your job, whatever you're trying to do. That's it. Just simple congestion. Yeah, that's true. But let's say that's about 5 megahertz. Same frequency, carrier frequency, but the frequency band, the bandwidth is different. Okay, so like that will be like 5 megahertz, I think, or 10. You can look into the numbers. My point is, nobody is coordinating that, right? There is no, like for example, in the case of cell tower actually schedules. So all of us are talking, as long as we are within the number of subscribers that cell tower can handle, we are scheduled. But in this case, there is no scheduling. because there is no central coordinator. So if everybody is talking at the same time, then what would happen? It causes congestion. So that is what is being referred to. Say again? Yeah. Yeah. So if it's a random access, then you will see collisions, right? That means if two people talk at the same time, then the receiver may not receive the data. Or you keep trying, nothing, just like and then maybe one of the times, it will be successful. So that's what I meant by congestion. Okay. So basically, we need to depend on, we need to have good communication support, reliable and resilient communication support, and obviously there are three solutions. We talked about mesh networking before. You can buy off-the-shelf radios and see whether they are sufficient. They are enough, but you have to be configured properly. It is possible. This is obviously a good solution, especially when cell towers are not present. And satellite communication is actually best, really speaking, because no matter where you are, you always get a satellite communication. But there are some situations like buildings or in maybe valleys. It is possible that you may not get a satellite signal. We have seen it many times. So each one has its own limitations. And then the best solution is to see whether you can combine them, complement, come up with a solution that is complementary. That means, can we add all of them? Can we have all of them? But that requires more payload. So you can imagine that solution. We'll going a little bit deeper and then see what are the issues. One is channel models. So it looks like, if you look in the literature, there are channel models. A lot of work has been done in terms of channel modeling, but still there was no need for us to think about air-to-air channel models at 500 feet or 600 feet or 4,000 feet. There was no need. And in terms of for aircraft, commercial aircraft, you might think, commercial flights have been running all the time, flying all the time. So what kind of thing they are doing? So typically the communication is through satellite, through ground control station. So as I said, even though technically it is possible for a pilot to pick up a phone and talk to the other pilot, those kind of solutions are not there, not being used. You only talk to the ground control station. And if you see in the movies, you will see like two pilots and two fighter jets are talking on the phone, but it is practical, it can be practical, but that's not the way we work as of today. And especially, you can make that happen. You can make that happen through, for example, through satellite. So it's possible that to support device to device communication either from cellular network or through satellite. It is possible. There's something called, if you look into the literature for 3GPP, you can see D2D communication, device to device communication. There's also called side channel communication. So those strategies are there, but they're not used as of today, as of now. So typical communication is through satellite to the ground, and then the ground control will talk to other. And in terms of channel modeling, see the need. You need to talk about air to ground or air to ground and ground to air. That's one channel, plus air to air. That's also necessary. The main point is we still need to do investigation or look into what kind of accurately modeling the channel. Until now, there was no need for looking at all these altitudes. Okay, but now air taxis are coming up, so we need to think about models at different altitudes. And then what about modulation techniques? If you look at 3GPP, the most commonly used modulation technique is OFDM or OFDMA, to be more specific. It is not only modulation, also is multiple access technique. So it is very powerful, and in fact, when I teach communication to my undergrad students, I always say it's a beautiful concept to use inverse Fourier transform at the transmitter and Fourier transform at the receiver. Now, if you look at OFDMA architecture, you'll see enjoy how nice, how genuine, ingenious that idea of using inverse Fourier transform for combining all the users' data, and then when you split, you are using Fourier transform. And it is very efficient in terms of spectral efficiency and all that. However, it is not suitable for satellite space communications or for drone to drone communication. So the new modulation technique is called OTFS, orthogonal time frequency space modulation technique, and a lot of people are studying that. It is very beautiful concept. The idea is you can design, if you choose the parameters properly, you can make it immune to Doppler shift. So Doppler shift is an issue when you look into satellite communications, like with LEO, for example, LEO satellites or drone to drone communication. It may be, we haven't done extensive studies, but probably it may be the OFDM technique may be okay for the speeds of drones, but we need to do more studies on that. But in general, Doppler shift is better handled by OTFS than OFDM. So we talked about the need for channel models and need for more advanced, more suitable modulation techniques for OTA communications. At the network layer, the issues that we are looking at are routing. And if you want to share information, with the dynamic changes in the topology, is it possible to implement standardized techniques like routing techniques that we are already familiar with? So routing protocols, dynamics of understanding the topology, especially dynamic topology, how do you model that? These are all issues that still need more research. Okay. So in general, we can. So in general, we will stop here at this after this slide. The key thing is insufficiency of existing devices and techniques, technologies, and even though in principle cellular communication or satellite communication are useful, but we need to design specific techniques for example, how to use device to device communication for drone to drone communication. So these are the, and in terms of maybe if you are thinking about satellite communications, is that latency sufficient? But again, on paper it is true that LEO satellite communication will have only little latency. Even for cellular networking also, I believe there is a number like 125 milliseconds or so. There is a return trip from a cellular from a 200 milliseconds. But on paper, but in terms of practicality, whether it could be whether it is enough for avoiding collisions. So that's the key question we are answering is that latency enough can handle the negotiation that are required for conflict management? That is the question that we still need to spend time. It's not that it is ruling out, but is it, on one hand, cellular industry wants to go for that, and they are actually working towards that. 3GPP has put a lot of efforts on non-terrestrial networking communications, but in terms of practicality, we still need to do more work, more experimentation to demonstrate that 3GPP or 4G or 5G communication is sufficient enough to provide the required reliability and resiliency that is required for drone supporting drones. So let's stop here and let's take a break here and then come back. I think this question on interactive session is better actually. All right, we'll take a break. All right, we'll continue this class for about an hour or so, an hour 15 minutes. So, in the previous session, we understood the necessity of V2V communications, and then how it can be supported through one of the ways, either mesh networking or cellular networking or satellite communications. So, assuming that you have good communication support, and what we will be able to achieve is this. These are the what you call outcome. Now, if you provide V2V communication, these are possible. So we are supporting through communications. We can support autonomy. You can provide some sort of a coordination among the aircraft, and you can enhance the situational awareness. You will be able to share information between the or among the vehicles, and to achieve some sort of collaboration. So just keep this in mind. All this is possible, provided you have some resilient communication support. So then, now we would get into how vehicles can communicate, and what do you mean by actually coordination, and we'll go into that levels, those topics. Before that, or before we get into the use cases or application scenarios, some performance aspects. What are the things that we are looking for? One is in terms of what we call some sort of a metrics. One is round trip time or latency, which refers to how much time it takes to establish or to send a message or to receive a message, because it's a two-way message. We are looking at two-way communication. Like for example, ask for you request for something and you get a response. So for that, how much time we expect. Second is the data rate and communication range, and obviously processing time also, it is not negligible, because once you get a message, the time it takes to process and respond, it becomes it becomes an important metric. For example, if you ask for a right of way, then the response time, which includes communication time as well as processing time, should be small enough to actually act upon the request. When two vehicles are coming close, then the difference or the time it takes to respond to a request becomes an important parameter. So these are the not what you call, these are simple metrics, not really complicated. All right. So the use cases use cases that are important for traffic management and collision avoidance are 5, and these 5 use cases were actually defined by RTCA. So the way to look at is, whenever you want to develop a standard, first come up with some small set of use cases. So these are the five cases that came from the people who are involved in the discussions within RTCA. Remember, RTCA is another standards organization. You can look on the internet, you'll see radio telecommunication for aviation, for aeronautical applications. Okay? So one way to design any sort of standards, not only for vehicle to vehicle, the process is start with some use cases, develop the standards, and then maybe if somebody finds more use cases, then you can refine those standards. Okay? So this is one approach, and it is meaningful actually. So for example, in the case of drone to drone communications, what we want to do is, okay, based on these use cases, we develop the standards, and then one day probably we will share with the society community and then ask them, can you develop a new use case, and then see whether these standards are sufficient enough, right? So we can open the standards for community and ask them to develop some use cases, and then see whether the current standard is sufficient enough. If not, we can revise in the next version. So this is a standard process, I believe. So what are those use cases? One is we talked about collision avoidance a lot. Then relaying the information. What do you mean by relaying information? You have something important to share, but the one vehicle that is close by probably may not be. So maybe one vehicle is close by, the other vehicle may not be close to the ground control station. So think about ground control station sharing information with the vehicles in the airspace. So first you talk to one vehicle, and the other one vehicle communicate with other vehicle, and so on. So point is, information relay is important for sharing critical developments in the airspace. Third is collaborative sensing. So this is also an interesting use case where suppose suddenly something happens and there is some weather development. Then what can be done is, all the drones that are in the airspace can sense from their perspective, from each of the drone perspective, and then collectively share the information with the ground, and the ground control station can assess the scope of the development, scope of the situation. For example, if there is rain, then maybe each sensor on each of the vehicle can estimate what is the scope of what is the volume of airspace that we need to avoid, and then share that with the ground. And at the ground control station, you can do the assessment and model what is the total extent of the scope, or total scope of the situation. Another example is, just in the worst case scenario, some drone is randomly moving around, then a rogue drone. It could be intentional, it could be unintentional. Intentional means something is happening and somebody is controlling the drone and randomly flying, or some sensor failed and the vehicle became rogue, meaning that it is randomly flying. So if that happens, it is very difficult for one drone to figure out the dynamics of what is happening in the airspace. So in that context, all the vehicles just sense what is going on, detect whatever they can, and share that information. So ultimately, you can see that in these discussions, what we are trying to get is, sometimes you don't even have to know what is the object, or you don't have to do anything other than defining the extent of the new development. If it is raining, we need to know what is the volume of in the airspace where the rain is falling, or if there is some sort of a congestion or anything, any development in the airspace. All we need to do is look at the volume that you are supposed to avoid. So the outcome is, you have to figure out how to get around it. You don't need to know what exactly is happening. So for such a scenario, collaborative sensing plays an important role. Fourth actually is very simple. We realize that all you need to do is maintain the distance between the vehicles, but what exactly needs to be done? As long as we know that there is a vehicle in front, and as long as we are able to detect its location, or learn the location of the vehicle in front of the current vehicle, then the response time is, to maintain the separation, all we need to do is, if the front vehicle is slowing down, you need to slow down. If the front vehicle is, if it is probably moving fast, you know that there is more space. So especially when the vehicle in front is decelerating, we need to maintain the safe distance, right? So you don't need to do there is no need for any other protocol other than just following or listening to the broadcast messages, and as long as you act on it, we are good. You don't need to do anything. But for other protocol, for other things, there are very defined processes. For example, how do you avoid collision? How do we share information? How do we do the sensing collaborative? For all this, there is a process. But for the maintaining this minimum distance, you don't need to do anything other than listening to the, for example, ADS-B output, and then maintain the distance. You don't need to implement any process. So we are going to see some of them. Okay, the first thing is basically collision avoidance is a situation, and then we identified about 3 scenarios. One is in one situation there are 2 vehicles in unstructured airspace, 2 vehicles in the unstructured airspace. That means they are not following any specific lane or path like this. So they need to figure out if potentially there is a probability of collision and avoid it. So how do you do that? It is by the way, all these use cases were studied in detail by my group, and obviously you will find more papers in the literature too. So this is the situation where the 2 vehicles are communicating with each other. That means they are friendly, they are cooperative vehicles, and through communication we are trying to avoid any potential collision. The only difference is, situation is that they are not flying in structured airspace. That's the only difference. So how can that happen? It is, if I'll give the outline, and then if somebody wants more details, you can reach out to me. So basically, each vehicle basically shares its current location and the direction it is flying is called heading, and the speed. So given that both vehicles are cooperative, it's easy to see each vehicle knows about the other vehicle's current location and which direction it is going, and then at what speed they are going. And you are getting the information about, let's say, once a second. Probably it makes more sense to see when the vehicles are closer, you may want to increase the frequency of these messages, right? Because 1 second may be too late. Again, in ideal scenario, the vehicles know about the other vehicles' information very clearly and most frequently. So then you can predict, you can do the mathematics to see how much time we have if you go in the same direction without changing, how much time it takes, and how much time you have to avoid any collision. So that is, I think, should be very clear, right? The challenge is to figure out is there sufficient time. That's one thing. Second is, between the time you receive the message or you send your location information to the other drone, and before the other drone actually processes the information, so that's where the latency come into picture. Do we have, are we sure, is there an assurance that, or is there enough time to, or is that latency is sufficient enough that your prediction is accurate? Because if you say you are at location X, and then by the time I receive the message and process the message and then try to respond in the sense act upon it, the other vehicle might move further. Right? That depends on the vehicle speed. So those specific issues we haven't addressed, but in general, through messaging, we can clearly understand that it is possible to avoid the collision. Correct? So that makes sense, right? Through messaging, all you need to do is just do the calculation and see how much time you have to avoid and potentially avoid. To avoid, basically you are changing your route, and because we are assuming that it is the traffic is not much, and because we are assuming it is free space, and it is possible to change the altitude, of course, change the speed or reduce the speed to avoid the collision. So one thing that's important here is, even though vehicle to vehicle communications provides a means to negotiate, you want to minimize the number of rounds of what you call interaction. You can't assume that you can't do everything through messaging only. So one way to minimize the number of interactions, number of round trips of messages is to come up with a standard protocol. For example, once we realize, once the vehicles realize that potentially there may collide, so what can be done is use some sort of a predefined processes. This I'll give you some example. You predefine the strategies, meaning that you're not asking what should I do. You're not that level of interaction. You are already predefined. If we find we are within the close range, then you follow probably. You can number. You can assign a number. So use process 1 or use process 2. So by doing so, for each of those numbers, you come up with a predefined way to avoid the collision. A simple example is if two vehicles are coming close, then maybe the one vehicle actually goes higher and left. The other vehicles go down and right. So that way, this is something like a military protocol actually. This will increase the gap between them. It's very easy to see that, one vehicle will go up and left, the other vehicle go right and down. So if you predefine this protocol, you don't have to negotiate. You just, okay, once you understand that there is a collision, probability of collision, and we're using this kind of a predefined protocol, you can avoid the collision. That's also there. Yeah, in fact, that's also possible. But this is one protocol I know from in the military. That's why I'm mentioning this. But in terms of, I'm not sure what solution we suggested, but in general, the idea behind this example, a scenario of crossroads that we presented is that they can safely navigate through intersection, or intersection is potential intersection, through messaging. So there's a possibility, right? And we are going to show later what exactly we are sharing in terms of. But the key thing is this: you define a protocol early on, and then one of the vehicles is going to maneuver. Basically, the maneuver process or maneuver technique has to be predefined. That's the key idea. Okay, you're right. So for example, in fact, the point that you mentioned, you will see in the next slides. So there are two techniques. One is you can change the altitude or change the speed, right? So this called, my students called velocity yield and altitude yield. But the next question is, which vehicle is going to, like in the previous example I was mentioning, okay, one vehicle go up and left and other vehicle go down. So which vehicle follows which one? Yeah, it's also there, but remember, if you are communicating with the ground, you are spending more time. It takes more time. So you cannot underestimate the time. See, a good example is, first of all, why are we doing drone-to-drone communication? Is to, like for example, I give always this example. Suppose you are in front of me. Why should I, instead of talking to you directly, why should I talk to take a phone? Why should I make a phone call? The phone call will go to the cell tower and come to you, right? Instead, it's better to have direct communication, isn't it? So the idea behind you to have a direct communication rather than going through the ground control. But it's possible, yeah. In fact, remember I talked about signal lights implementation of there is no other way other than going through the ground, because I don't think there is any other method to detect there is a red signal or a green signal. The only way is to have a centralized control. But here the point is, you want to avoid centralized control. Right. Yeah. That's right. Exactly. It is if you are doing in a 3-dimensional. That's it. in 2D, you will say, oh, you always have the one which is overtaking. You have to go to the right. Yeah. Right. Yeah. Right. Yeah. No, actually, really speaking, there is no, none of these are standardized. So even though I'm giving an example, but what I'm trying to, right. Yeah, these are not there. Nothing, none of no standards were developed. I'm referring to no. Once I was at Air Force Research Laboratory, and I was mentioning about 10 years ago almost, talking about this drone-to-drone communications. Another person said we need such standard because this is what we do in the military. So that's when I came to know that there is such a protocol in the defense. Hmm. Hmm. For now, there are no lanes or anything, right? We're just assuming two vehicles are flying freely in the free space. There is no structure or anything in the airspace. Yeah, right. There are two drones coming from different directions, and if you don't change anything, change the direction, they will collide. And that kind of that you are first figuring out. Okay, there is a potential collision based on your trajectories, and then well, I mean, in the sense, basically, you are leaving to the vehicle to figure out. Yeah, these are these circles that are actually showing the sensing area and communication range. Sensing and communication. This again? Right, yeah, communication is a bigger one and sensing is this. Yeah, you're right. So that's the idea behind the diagram actually. Mm-hmm. Right, they're so yeah, no, so here first of all, in this case, yeah, let's think about it. So when suppose we plan everything ahead, right? You don't expect this. When you plan everything and everything goes well, you don't expect. But this is a scenario when even after planning, because of some situation in the airspace, you are seeing them together. You're seeing the potential of collision. It's not that, let's call it as a tactical deconfliction. We talked about strategic deconfliction and tactical. Yeah. Yeah, that was, yeah. We don't know. Yeah, that we don't know exactly what is still the reason, but one of them is a military vehicle. I heard. Yeah. One of them is a, yeah, and maybe usually military vehicles are given more freedom in terms of choosing, and something major went wrong actually. But here the scenario is, well, I mentioned in the morning, there is a traffic management system. It's like a service, and so it is managed by so like whoever is by companies. There's no aviation administration for the drone traffic management. It's all done by private entities. But as you said, as you asked in the morning, what if two companies are flying their drones, individual drones, right? So then there is a coordination. Actually, there is a what you call well-defined coordination. There is a service called directory synchronization and service. What it does is, before you start flying, you have to get approval from that service, and the DSS system will actually record anything that is going on in the region, whether the flight is coming from some other region or this region. It keeps track of those, what I call the flight trajectory, or something we call flight volume. So these are, by the way, practical. It's not something in theoretical. B2B standards are theoretical, but the traffic management and then how all the services work together to make sure that the flights are not overlapping or clashing, that is very well defined through ASTM standards. ASTM is a society just like RTCA, another organization which is developing the standards, and it has been tested also very thoroughly. So we are comfortable with multiple drones flying in the same area by different companies. No, we are okay. We are able to handle that. Again, how do we do that? Whenever you are flying, whenever you're about to fly, or whenever you need, you plan a flight a mission, you're sharing the entire path with an agency, with a system. And it's something like white pages. We call that as a white page, like a directory. So every company is supposed to register with the oh, this is my flight plan, and what do you have in the flight plan? The exact points, from where to where you are flying, and timings for each of the points each of the waypoint. The other option is the entire volume. You're saying, oh, this volume I'm going to fly from time t to t0 to t1. So basically you're reserving. It's more like a reservation. So once you reserve, then any other flight that is coming to the same area, same region, doesn't matter which company it has to get approval. It has to make sure that it doesn't clash. And that kind of resolution, or what I call the deconfliction is managed by this, and it does only that nothing else. So there is a specific service that handles this kind of resolutions. So with that, it's very effective, and it is, yeah. Right, those things. Sure. So that's the point. In fact, this collision avoidance is in the airspace, close encounters, and actually we can also assume that you don't have time to talk to the ground control station. That's the key thing. So direct U2U2 communications, and what we did is, okay, using these use cases, we only talked about only one, but using the use cases, we came up with a set of messages, including the content, exactly what information or what fields we want to use, and then design this protocol, this standard. And so now interesting thing is, we start with a use case, develop the message protocols, and then ultimately your protocol is independent of the use cases. See, you're not saying, oh, my message structure will only applicable for 1 or 2 or 5 use cases. That's not the intent. To begin with, you have these use cases, we build the standard set of messages, and then say we push aside these use cases. The reason is, for any new use case also, there should be this message protocol should be sufficient. Like, for example, let's take TCP/IP, so or those kind of UDP protocols. You cannot say that UDP message protocol is only applicable for sharing files. Which is also, maybe at that time when we were developing TCP/IP, we didn't even know that HTTP is going to come. But see how TCP/IP is enough, or UDP is enough to handle HTTP thing, right? So any future use cases also we should be able to handle. But if not, what happens? You get a new version, new revision, right? So ultimately, even though you begin with the use cases, the standard should be independent of the use cases. We're not catering to only limited set of use cases. That's a key point. So that's the approach actually we're following. Anyway, so I hope you understand the crossroads scenario, and the second and third are more structured airspaces. So all these are related to collision avoidance, but the second use case is something called merging. So it's very interesting, and really speaking, one of the undergrad students who came up with the solution for this. And I'll explain merging, and you will see why this is a bit tricky, and how and I'll show you how a student was able to handle that in a very simple. Remember, your protocol should be very simple. We're not trying to negotiate 100 times, because it should be done in real time. It should be done quick, and with minimal interaction, between the drones. Otherwise, it will be, if it takes time, each round of communication may delay things significantly. So merging is very fast, very, very interesting. So what we are trying to do is, here in this use case, of course it is structured airspace as opposed to other. When one drone or one UAS wants to merge or change from one lane to another lane, okay? And there are other related scenarios. For example, let's look at a scenario where, okay, there are flights going in one lane, and there is a new drone that is taking off from the ground and entering this lane. So that means it's almost like entering the highway. So when you enter a highway, you want to make sure that you have enough gap to get into, right? So in one scenario, maybe if you don't see anything, yeah, you're good. You just fly and get into the lane. But if you see there are busy traffic, let's say, that means there are vehicles in every cell. Then how do you get in? So that's where the innovative idea came from one of my students. We'll get into that. Another scenario is something called roundabout. This is by another undergrad student. In fact, most of the contributions actually came from undergrad students. So what is roundabout? You might have seen circular intersections, right? Very, very common. In circular intersection, the rule is the vehicle that is already in the circle has a priority, right? That means if you are entering the circle, you have to make sure that you are yielding to the vehicle that is already in the circle. So you have to find a gap. So basically, the one that is entering has to find a gap. But while exiting, exiting is easy, because exiting, again, while you are exiting also, yeah, while you are exiting, by the way, the exiting vehicle has to make sure there is no cross traffic. So while you are entering, it is the vehicle that is entering has to yield for the traffic which is already in the circle. When you are exiting, first of all, it should be easier than entering. The second thing is the exiting doesn't require that, it's not complex. So let's focus only on the entering part. So this is a simple example of, even though it is not dark in color, it's very light color, but this is an intersection. And at some point in the very early stages, we were thinking multiple levels. But what we were told is that you can't expect a lot of airspace, and multiple levels probably is not a good idea. It doesn't mean that it is we put aside, but the key thing is you can't expect so much space in the air to introduce multiple levels of. I haven't seen any. Only probably some people might be thinking, but it is not practical in what we were told. Anyway, we'll elaborate on these use cases one by one. Yeah, I think we're explaining the use cases, more use cases before getting into details. Minimum separation, we briefly talked about it, but the key thing is, again, in the structured airspace, we want to maintain minimum spacing. I think here is an example. Information relay, we talked about this before, but we will go into a little more detail. What exactly you mean? Allows multiple vehicles or two vehicles to communicate beyond radio line of sight. This is also called BV loss. BV loss is beyond visual line of sight, and beyond radio line of sight is BRLOS. Collaborative sensing, little more detail, more well-defined details. Allows UAS to gain greater spatial awareness or situational awareness. Typically, this is for sensing the hazards, and sometimes the hazards are bigger in scope. So that's the reason you need to have collaboration, right? There is a term called constraints. Constraint is it is used for describing what we call no-fly zones. A constraint is an area defined by a volume of airspace that we are supposed to avoid. So that's called constraint. But in simple terms, it's like a no-fly zone. Don't go there. That's what he said. No-fly zones don't have to be only because of something that is happening in the air. It's possible that maybe a fire on the ground or a big public event that is happening on the ground, you want to avoid that area of airspace, corresponding airspace. So the point is, in general, no-fly zone is can be defined at any given time, not only before the flight takes off, but it could be developed, it could be defined while the aircraft in the airspace. So in simple terms, it's the no-fly zone can be defined in a very simple manner. To just give an idea, how do we define? We define it like a cylinder. So, and the simplest way. Remember, it's not just what you call the mathematical genius, that what you call mathematical precision that we need. What is more important is how practical it is to implement. So for example, how you define a airspace, and you can define a very irregular airspace in multiple ways, but the easiest way to define airspace volume is through regular shape. The easiest shape is define a polygon or a circle, the two options. You define the base and roof, ceiling as a polygon or a circle, one of them. In case of circle, you are taking a center point and the radius, and if it is a polygon, you are giving the points, 4 or 5 depending on the shape. And then, so once you define the polygon, which means that you are defining both the bottom and ceiling, floor and ceiling, the same polygon. You are assuming it's the same. So basically, you are defining a regular shape. The second thing is, all you need to do is define the lower altitude and higher altitude. So basically, you are defining the polygon and the altitude, two altitudes. One is lower and one is higher. That's the easiest way to define, and that's how our standards are defining. So that's that what you call may not be very. It's not very precise, but it is the best way to define, really speaking, with simple, in a very simple manner. Okay. So we do that. We call that as constraint or no-fly zones. So remember that the key point is make it simple. Well, keep it simple. I think that's the right way to say. So that's I'm trying to explain what do you mean by constraints, and that's and the final use case is rerouting. Rerouting is in the middle of the flight or dynamically changing the current flight plan in the middle of the mission to avoid any constraints such as weather or any no-fly zone that is defined in the middle of the flight. So those are the use cases. So basically, we discussed all the use cases, but now it is time for us to look into maybe a little more into the strategies, and finally we want to look into the message protocols. The ultimate goal for the standard is to define the messages and formats very clearly, because when we define the standard, we should be able to implement it, we should be able to program it, right? Or for automation point of view, autonomy point of view. So which means that the processes have to be simple and everything had to be explained very clearly. For example, each field, what does the field means, what are the possible values, all those things have to be very well defined. At the end of the day, on top of or using the use cases, we are building these protocols, collision avoidance protocols, or all the things that we talked about, rerouting, minimum separation, all those things are defined based on these messages. So two things are left for now. One is what are the messages and what are the content of these messages, number one. Number two is how to define the protocol using these messages for different use cases. So these are two things. The third thing is later, and we will worry about that later, maybe in future during these remaining days, is that, remember I was talking about developing a model that will allow us to define the communication range plus how far, what will be the signal strength at the receiver if you use a particular, if you define the transmit power, like say if I use 1 watt, then given the frequency and given the transmit power and the channel model, how far we can communicate. So that's a different thing. So for now we are looking at only application level, but we will get into physical layer issues later. Yeah, I would, even though there are some terms like floodcasting, I will avoid discussing them to keep it simple. Yeah. Okay, we already talked about this. I will move forward. So let's look at this message protocol. Try to, I hope you are able to see this. Let's, okay, I will read it for now. This, I think the slides will be given to you at some point. So in this is, I think, very generic message structure, and let's focus on the higher level. The first message is called discovery message. Discovery message, and there's one specific type of message called right of way message. So discovery and right of message. So I'll describe what they mean, what is the intention behind them, and then we will see whether we are able to understand the spirit behind this. Yeah, like it's like a broadcast message, something like ADSB. Discovery message, something like ADSB. ADSB is every drone or every vehicle is sharing its current location, heading, speed, and the minimum details. Of course, it also includes vehicle type, what vehicle ID. Vehicle type is also important because whether it is a large vehicle or a small vehicle, that depends on the vehicle type. So vehicle type, vehicle ID is like a license plate. Okay. So you are defining, you are sharing what type of vehicle it is, and what is the ID. The ID is something like a registered number, like a registration number, right? So our license plate. So with that information, you have the basic details that are necessary for what you call implementing any of the use cases. Okay. I see. Okay. All right. So you can see the vehicle name. We are getting into the fine details. Okay. Vehicle name, vehicle ID, priority. We talked about this before, because if you know that the other vehicle is high priority, then you will yield. Okay. Otherwise, you expect the other vehicle to yield. So high priority vehicle or low priority vehicle will yield to the high priority vehicle. So all this is done by protocol. All we need to provide is give the priority number here. So once you send this broadcast message out, then the other vehicle knows that whether your vehicle has a high priority or the other vehicle. So that is the idea, So many of the things are predefined. That's the best way to handle the protocol. Otherwise, if everything you have to know in the air while you are in the air, it is too much. You cannot you cannot satisfy the real-time requirements. Okay, so most of the things are predefined. So priority 1 means maybe it's like a medical service. Priority 2 means something different. But the meanings are well defined. And also role. See, these things are not there in ADSB. We talked about before, but it is important for implementing this collision avoidance and other kind of use cases. You need to have more information. Role is, we'll look into all the details, one by one. But here, role refers to, are you the leader? Suppose you have a formation like a group, then are you following any specific role? Are you having any specific role in the mission? So, for example, a leader, something called wingmate in the case of military applications. Now, one of the companies that is involved in this process is a company called Unmanned Experts, a startup company. The CEO of that company he worked for Royal Air Force. So he added some of these military application. There's something like a swarming. If there is a swarm of drones, there will be a leader or maybe a follower, leader or follower. So leader, basically you're defining the role of the vehicle, more like a futuristic. Probably we don't need for civilian application, but this is something like for future. So at least for now, we are not expecting what you call leader follower or fleets of vehicles or swarms of vehicles. But for futuristic point of view, we define something called role. And then port is like IP port. And one thing that happened is, because there is already a remote ID standard, we have two options. Either we use it as it is or not use it. So, but we are not supposed to change an existing protocol, existing standard. So once there is a standard, you cannot come with another standard to undo things. So in that spirit, remote ID is used as it is. So I hope you know what is remote ID. We talked about this before. I think it's also something similar to what we are calling as a discovery message. But the details that we have, the information that we have in remote ID are not sufficient. Yeah. All right. We talked about the information at a high level. Okay. Then in the next row, there are little more details. Like so, look at vehicle ID. The vehicle ID contains vehicle type, mode, state, intent, status, and action. So this is a lot more details than any of the existing standards. Here we are looking at what is the type of the vehicle. Why do we need type of the vehicle? Based on that, for example, is it a fixed wing, or it is a rotary, or is it eVTOL? So even though they may not be used in every use case, but it's important for a futuristic point of view to describe the vehicle in detail. Priority is high, medium, low. I think at this point we felt the three are sufficient. Is it high priority or medium or low? And telemetry is also kind of a standard in the literature. Timestamp, latitude, longitude, altitude, heading, bearing, and speed. So in fact, really speaking, this information is sufficient enough for us to understand the idea behind this message. But obviously, when you are writing, when you are a programmer or trying to implement, when you are trying to code, all these details are also necessary. Okay. So let's look at some of them. Yeah, status. So let's look at the one of the fields, status. So status refers to what exactly you are doing now. Okay. Some example is yielding. I think this is something that you can see. Yielding means you are saying that currently I am yielding to other vehicle. So that explains the idea of status. I didn't explain other things. So basically, status refers to what exactly are you doing in the current situation currently. So one example is yielding. So which means that if you see status equal to yielding, it means that okay, somebody asked me to yield, I'm yielding it. So remember, yielding happened before, right? We talked about this before. In crossroads, if one vehicle can ask other vehicle for right of way. So when a vehicle requests for right of way, the other vehicle responds by honoring the request, and in response, the second vehicle is supposed to yield. So the yield could be changing the altitude or changing the speed. So that's in that context you are saying yield. Another example is while one vehicle is trying to merge into the lane, then one of the vehicles in the lane is yielding, so and giving gap so that other vehicle can join. So that's also kind of yielding. So depending on the context, the meaning of yield probably slightly different, but definitely we need such low level details. Another example is emergency. That means currently some emergency thing is happening. For example, maybe a vehicle is landing for lack of battery or for other scenarios. It's an emergency mode. So basically, the vehicle is in emergency mode. So that's the idea of status. And there is something called mode. The mode is I look at only some of the. So it says mission. Mission means it's a specific mission. That means it is not independent, not autonomous, but it's part of a team that is trying to achieve some goal, achieve some purpose. Corridor refers to okay, I'm probably, the corridor is that you are flying within the corridor. So some of them may not be so intuitive, but some of them, these are designed in such a way based on our understanding, the people who participated in this working group, based on their understanding, they came up with these values. Okay. Let's take some more examples. Yeah, intent is another point. The intent, state intent, the intent is, yeah, you're trying to tell, it's like another level of information, another piece of information in addition to mode and state, your intent, and that means what is your, what is that you're trying to do in future. For example, here, to resume, to return, take off. Yeah, this is a good example. Take off. I'm in the process of taking off, which means that what it means is taking off has a different, what you call different, changing altitude, right? When you take off, you are actually changing the altitude. Whereas if you say I'm in normal mode, then that means you're not really going to change the altitude. So those are the fine details that become important, if not for one particular use case, but for others. Okay. Return is maybe you're returning home. Return, right? Hold, probably hold means you are on holding pattern. So these are the additional details that we were able to figure out. And then you don't need to fill up every field. Only depending on the use case and depending on the context, it is sufficient to fill some fields and leave others open or blank. When you are processing these messages, then obviously depending on the context, you know exactly what information you are looking for, and you only look for those fields. So just because it's not redundant, it's not waste of space, but keeping the intent, our intent is to make sure that this set of protocols or set of messages is sufficient enough to handle every use case. Okay, some of them are defined, 5 use cases are already defined, but in future there may be more use cases. So maybe I think there is another thing, action. So action field refers to, yeah, for example, here there is a sensor, start and stop sensor. All right, we'll stop here. I think we gathered or gleaned enough information to see the meaning and purpose of these messages. So this is a broad picture. Okay, in fact, really speaking, we're not defining the protocol here. We're defining only the message structure, messages and the corresponding fields. All right. So one use case is we call that merging, and in merging, the key idea here is you are going from one lane to another lane. For example, this pink color lane, there is a drone. It is trying to get into southbound, actually sorry, northbound. So it is going from, or maybe this way, a northbound plane is trying to enter into another lane by turning 90 degrees. So a vehicle is flying towards north, going towards north, and is trying to move on to turn 90 degrees and get onto this lane. I'll give some details to understand, appreciate this concept here. So he's saying top layer is northbound, and this is southbound, I believe. So there are 2 lanes, one going towards north and one going towards the south. Bottom layer is east and so this is east and probably this is west. Middle layer is turning layer. Again, remember, this is all hypothetical. Okay, these are not, we don't know whether this will be standardized or not, but this is just an academic exercise. We published a paper, peer-reviewed paper, conference, but potentially if this is accepted, it will be followed by in the aviation industry. But we are too far from that, from reality at this point. Okay, but obviously, if at all we come up with this multi-layer structure, and if this we define these intersections in the airspace, yeah, this is one strategy and solution. And there, we also assume there are some sort of a exit and entrance ramps, something similar to ground. So you see the big picture here. We have three layers actually. Top layer is north and south bounds. So this is north and this is south, and if it is, yeah, if north is in front and south is in back, then this direction will be west and this will be east. So this is actually west and this is east. Okay, that's the idea. In the middle layer, it's like some sort of a room for going up, climbing up, or climbing down. So in that scenario, you identify about 8 conflict points. So and you can see this 4 in the inside and 4 outside. And you can see the maneuvers. For example, when the vehicle going towards west is trying to go to north, it follows this arc, and you can see similar things. Right, the arrows are clearly pointing out. Now, hopefully, you share the slides soon. Then you can see. So it's a beautiful, just what you call a thought process. So that you are trying to create an intersection in the airspace. Okay. Okay. So we didn't define the exact protocol, but we'll come to that. How do you merge? That part we'll do that later. I'll go into details, and it's a very well explained, very well conceived. But generally, you are defining maybe the summary here is we are defining what you call the structure in the airspace. That's it. Okay, we are defining these artifacts. What you call intersection. But we didn't define exactly how do you merge. That's a different, that part comes late. Okay. Before we go further, this is another concept that we came up with. So once again, it's all hypothetical. If you think, oh, is it going to be implemented? We don't know. Okay. But papers are published. Because this is all academic exercise, we have the liberty to think. So another concept that we came up with is something called air cells. Very beautiful concept. It will facilitate automation. It will make the traffic management very efficient if you follow this. And there is a lot more to think about, really. I'll present those ideas. First thing is, what is an air cell? An air cell is a derivative of something called geofence. If you type geofence on Google, you will see it is defined in the context of aviation or unmanned transportation. There is a professor from University of Michigan, but now she is chairing the aerospace department in Virginia Tech. I had an opportunity to interact with her, and she introduced the idea of geofence. So I talked to her and say, I'm using your idea to define something called air cell. Her name is Ella Atkins. You can ELLAATKINS. If you type geofence and Ella Atkins, you will see very beautifully explained definition of geofence. It's a very mathematically defined. So what we decided is, so I said I'm going to use this. So how do I present? She said, present your air cell as a derivative of geofence. So because remember, whenever you are trying to work with a new concept, you have to be careful. Number one is make sure that it is consistent with the vision the other person has. And the second is it should be in alignment and also consistent, and you should be advancing our field. Okay, you can't define something. You can if you there's nobody stops, but it's better to look at the literature and make sure that you're following those guidelines and ideas that were defined before us. Okay, so in some sense it is like a geofence. So what do you mean by geofence? So of course it is virtual. You're defining the boundaries. Okay. In case of geofence, actually it is not, there could be static or dynamic. So one way to visualize geofence is, the idea behind geofence is that when a vehicle is flying, suppose there is a vehicle could be anywhere in the airspace, and then you define a boundary around you, and you declare that this is a geofence. So follow this. There is a big difference between air cell and geofence. A dynamic geofence is, an example for dynamic geofence is, a vehicle will build a bubble around it, and then that calls it a geofence. So what is the meaning of it? It makes sure it protects its space. It allows us to protect the space, meaning that no one should come within my space. If you do, if somebody comes in, you potentially there is an accident, right? So especially for a free space environment, we talked about before, rural areas where you don't have structured airspace, this geofence concept is very powerful, and it is moving. It's a moving geofence. So when you are moving, your bubble will move along with you, and the rule is no one should enter into this area, into this bubble. And why is that? Because that will provide you a guarantee or assurance of safety, right? But how to implement? Let's put that aside. That is challenging. How do you implement? There are probably many ways, but point is, it's a responsibility of maybe not only the vehicle but other vehicles also to respect the boundary. But if it is, there are many situations or many what do you call, derivatives. It's possible that other vehicle is non-cooperative. So what do you do? So those are there, but at least you are defining a means and ways and means to assure safety. Okay, I hope you followed what is the meaning of geofence. Yes. Yeah. No, it is no, not man. Nothing to do with this. It's just a boundary, you know. I don't. I mean, I understood the spirit of it, and because we use this in our work, and I had a one-on-one conversations with the professor, but I don't know beyond that. But it is a point is very well defined, and you can program it. You know, it helps in autonomy, and it helps in assuring safety. That's for sure. It is very significant. Yeah. That's right. No, well, no. By the way, this boundary is defined by me. Air cell is, but geofence is very flexible. It could be any shape. All you are defining is vertices. So it doesn't define. It doesn't restrict to circle or prism. So yeah. So the reason in fact, I'll tell you a little more about it. So I thought, let's consider like a prism, okay, rectangular prism. So that's how I defined air cell. So air cell is defined by me and my students. Geofence is more generic, and as I told you, by talking with the professor, I was able to make sure that we are respecting the invention that she had. At the same time, we're also not deviating so much from the original idea. Okay, but then look at this. I thought, okay, let's use this. Like I thought it's like a cube, but one of the colleagues said, let's keep it like a prism, rectangular prism. And then I wrote a proposal based on this idea of air corridors and all that. Probably I didn't define air cells at that time, and I got a good grant, $1 million grant. It's called Resilient Intelligent Next Generation Systems. And I had another partner who is from University of New Mexico, and then I said, okay, we are working on corridors, but he took off from there. He came up with his own way, and he suggested the corridors have to be cylindrical. So probably maybe he is thinking along the lines you are saying. Circle is an easier way. But then, okay, that's fine. So both of us are defining our own ways of what definitions of air corridor. But then both of us are within our scope is for mobility. We are actually facilitating mobility or traffic, right? And so maybe you can also think about control or how to manage the traffic. When you take management and traffic, obviously it's something to do with controls. But then there's another development that happened. See, this is the reason why we have to keep open-minded, keep our minds open, also read and read the literature. From communication point of view, there's another concept of air cell that came up. I talked to you before. The idea is, how do you divide the airspace, something into like tessellation, concept of tessellation. For on the ground, for cellular networks, you define your coverage area or tile the coverage area using hexagons, right? Those who are looked into cellular communications, you will see that to understand the coverage, and especially for frequency reuse point of view, you define or tessellate the space in terms of hexagons. So hexagon is a basic cell. Similarly, in 3D space, two professors who came up independently that the airspace in 3D airspace could be divided into cells of shape octahedron. So the point is, from communication point of view, octahedron is a basic cell, but from a mobility point of view, we consider like a rectangular prism or maybe cylindrical. Both are fine, but either way are fine. Basically, mobility point of view, all you are facilitating is how can I show traffic in this structure. It could be a cylinder or maybe rectangular prism like this. Okay, but potentially, is there a way for us to look into satisfy both, or maybe which is better? Which is, well, not a question of which is better. It's from communication point of view and developing the concepts of frequency reuse. It is octahedron that makes more sense. But for simple mobility point of view, this is the idea. Anyway, I wanted to share with you the structure in the airspace also is evolving, and before I started this work, there was a book that I followed, I saw, where some of the ideas about structures in the airspace are talked about. It's called lane-based airspace management or something. So basically, lanes are defined even before we started working on this. So, but the nice thing is, it's all the problems are, there are so many open problems, and there is room for invention and doing something new. But this works very well. So what we did is, going further, we defined how we can manage the airspace efficiently using this basic unit air cell. So for example, only one drone can occupy one air cell at a given time. That assures you that by design we are avoiding accidents, we are avoiding collisions. Now, which means that if you enforce, again, enforcement itself is a challenge, but somehow if you enforce that only one vehicle can be in one air cell, that guarantees that by design that there won't be any accidents. Accident means everything is going well, but you're not trying to pack, you're trying to avoid a scenario where two drones are coming so close. Okay, I hope you see the point, but then we can discuss it later. And then waypoints. What is a waypoint? We talked about before. If you are defining a flight path, the flight path will be a set of flight paths consists of set of waypoints that you are supposed to pass through until you land. So from takeoff to landing, you are defining which points you have to touch. Obviously, it's not possible to exactly follow the points. Okay, but the point is, that's your path. You're creating a path through some sort of a straight line segments, but then as much as possible, the vehicle is trying to follow that. So just like the way, remember when you see a airplane landing, after landing, it's supposed to follow a straight line, but it doesn't mean that it's going to exactly go on the straight line. It may go wayward, but the goal is to follow the straight line as much as possible. Even you drift once, you want to come back. That's exactly the point. Okay, but so what? Again, my students worked on this. The waypoints represent the centers. So that means we are saying your path actually is that goes through the centers. So these are the waypoints, but you have the wiggle room to flexibility to move around within that area. So in fact, it doesn't make sense for to define the path very rigidly like this. So you need to define, you need to give room for moving around. One more thing is the air cells are static. Notice that now I talked about geofence, which could be dynamic, but these are well defined. That means you can, these are like markers. You can say we can say that I can give ID. This is number 1, air cell number 1, 2, 3, 4. You will see more challenging issues if you really get into the into details. But point is, you can give assign IDs. So which means that what is the benefit of this? You're looking at, if you look at your screen or your command and control center, you know exactly which vehicle is where. See how is very clearly you can see that how airspace could be managed. And again, this is only a vision. This is not something that is that it potentially may become may be followed, but there is no guarantee that aviation people will like this. And but generally the idea is to have a, it's not like control, but it's more like knowing exactly where the vehicle is and how to manage the traffic, how to manage it efficiently, and how to minimize the potential accidents and all that. Okay, that is the spirit. And that lot more than that. In fact, I'll give you little more details. So for example, you can also have a data structure. Every air cell will have information about it, meaning that follow this carefully. So let's say what is the weather like, what's the temperature, right? So if more interestingly, if a vehicle is passing through it, if you have a sensor on the drone, that information will come to the ground because it's sharing the telemetry. So you can add temperature information. So in addition to the telemetry, along with the telemetry, you can add all those auxiliary information. What was the experience? What did the vehicle sense while it is traveling through this? It could be temperature, it could be pressure, it could be many other things, right? Rainfall, for example. So think about a data structure associated with this object. So if air cell is a class, they're all objects, and every object will have information about the object, like all those attributes, right? Not only that, you can also see how occupied is that cell. I mean, currently it is occupied probably, and then how many vehicles pass through that air cell for the last hour. You can compute. Basically, it helps us to what you call measure the traffic. How many vehicles have passed through for the past 1 hour? So that means you're actually measuring some parameters associated with the traffic. All that is possible. That's because of this simple structure that we are defining. Okay. So I think. In fact, yeah, we can take a break here. So I think I'll wrap up just with one more point, is that we filed a patent on the concept of air cell, and the paper that we are publishing, we prepared, is on hold. We are waiting for the patent to be filed. It's in the process actually, because if you are filing a patent, the paper should not be published. So some of the information is still in the paper. We are about to publish, but then we are in the process of filing, and as soon as it's done. So the point is, because these are new ideas, there is a room for creativity and innovation, and then once again it's undergrad students who are actually championing this work. So we'll continue this in the tomorrow's class.
Okay, good evening. I will start now. And today I'll be talking mostly on topology management and routing of message in the network. So if you try to see the wireless networks or any wireless communication system, the wireless links plays an important role. And the stability of the wireless link is random in nature. They are not fixed, like you cannot guarantee anything for a given wireless link. And designing a topology or defining a topology for that random links is very difficult task. It is not a simple task. And the another difficult problem is, for example, if you have a wire, you can transmit through the wire and get back the signal in the same path, so the path distance is constant. In a wireless link, it is not constant. Even if it is line of sight or non-line of sight, the link might go in, the signal might travel in one direction and the return signal might travel in another direction. It might be a reflected path, reflected from some body, and you get it. So the paths are not identical. So it makes more difficult than the wired networks. So the difficulties are the wireless communication, the links are unstable, they are random in nature, they are uncontrollable by human being because there is an environment which affects it, it is a rain which it affects it, or there is an obstacle which will obstruct. And we don't know whether the packet has been delivered properly at the other side or not. There is no guarantee that the packet has been delivered safely. In a wired link, we can hear the collision. The signal, we can observe it. In a wireless link, even if you try to observe it, you will not get it because the signal is traveling apart. So with these difficulties, if you want to define a routing algorithm or define a topology and then design something is very difficult, because in this instant, you might have some structure and the next moment you will have some other structure because of the instability in the links. And this might also create a partition in the network. The network might be isolated, like some nodes might be isolated, some might be connected. So you might have more number of isolated nodes than the connected nodes and so on. So what we try to do is we'll try to understand the wireless network for some time, and then we'll try to develop the routines for such type of networks. So in basic system, if you try to see, the wireless networks, we classify them into two groups. One network is you have infrastructure support for the wireless network. The other one is they don't have any infrastructure support. For example, you have a mobile network. The last piece is only wireless. The base station to the user equipment of the mobile is only wireless. Rest of the thing is wired. You take a Wi-Fi network, all the behind the access point, everything is wired. And only before that, only the wireless access to your user device is wireless. So such type of networks, we call it as infrastructure support networks, right? So the examples are cellular network. It can be a satellite network. Satellite network also have a base ground network to which the links are connected. The end device is only wireless. The rest of the things are all wired. Similarly, radio network is again a wired network. Only the antenna which transmits the signal to your receiver is only wireless. You take television, it is only infrastructure support. Only the signal traveling from the antenna to your house is wireless, rest of things are wired, right? So most of the networks, what we are trying to see comes under this category, infrastructure support network. Now, if you try to speak about the current topic like drone networks and all, it doesn't have any support, right? It has some links to the ground, but it doesn't mean that all the drones are connected to the base station. Right? There are some drones which are not connected to base stations. They are only using hop-to-hop links from one drone to other drone to other drone and so on. And they are trying to maintain the network connectivity, right? So we refer them as ad hoc networks where there is no support of any infrastructure. We refer such type of networks as ad hoc networks. Like for example, you have a Bluetooth in your laptop. You connect 7 or 8 devices, the keypad, the headphone, your mobile, everything you can connect. That is a ad hoc network. It doesn't have any structure. You can keep your mobile here, you can keep it here, you can keep it somewhere else, around the communication range, wherever you want to, you can. Similarly, I can put the headphone, I can move around and still get connected. So these devices which don't need any infrastructure support, we refer them as ad hoc network. And a very good example is a wireless sensor net. You throw the sensors in the agriculture field or someplace and try to monitor the situation, right? So we classify these wireless networks into two parts. One is having some infrastructure support and they have a constant link with the infrastructure. The other one is an isolated network which doesn't have any backbone, doesn't have any structure, no topology, nothing. We call it as infrastructure-less network. And that is what we are trying to concentrate now. So this is a good example of a cellular network where you have the base stations around. You can see that there is a base stations, and these base stations are connected to the mobiles are connected to the base stations. And these base stations are tied together to a switching center, and there is a fiber which is running to the base stations, right? And you can see clearly that you can expand the network to any extent because the fiber you can run it for kilometers. Okay, and designing such type of things, or designing a routing protocol structure is very easy because these stations don't move; they are fixed. So now you know the structure of it, right? And designing something on that structure is simpler than something which is moving, right? The next is similarly satellite network. You have ground station to which these satellites are connected. Okay, these links are wireless, but they are connected directly. And there is a backbone which is trying to connect all the base stations and to your central switching system or whatever it is. Okay. So even if this link is there, if you have a dual link, automatically the satellites are still on. Okay. And similarly, in this case of mobile, if this link is not there, if you can get a link from this mobile station, still you are on. And even if you provide mobility for these devices, there is one base station where you will be roaming around and you will get connected, right? So the design of cellular networks or satellite networks or infrastructure networks are much simpler than designing a wireless network, ad hoc wireless network or mobile wireless networks, where there is a mobility and there is no infrastructure support. They have to talk in group and move around. Now, for example, I think you might have seen that you are four from one university and you are moving around in the campus. You don't go in a distributed manner. You go in a group, move around, talk to yourself and see where you are and come back, right? That is how the ad hoc network tries to work, right? If it is you are in your place, you have infrastructure support, you have your college support, you can do whatever you want, right? So the next example is ad hoc network. You have different devices which are moving around. You call it as IoT device or drones or whatever it is. And you want to connect them together. And if you want to apply the knowledge what we have in the wireless wired communication into it, it is good. You can connect like a mesh type of thing, or you can connect like a star with a central hub, put one drone over here as a central one and connect all to that. Or you find a tree type of thing and so on, you can do it. But now doing that will help us in finding the topology or not is the prime question, right? And now once you form a static picture of it, assuming that it is a mesh network, and that network is valid as long as the other drones are in the communication network of each and every drone, right? So you have to be very careful when defining it. You have a drone A, and you can say that drone B can hear you if you are in the communication range of A. If you are inside the communication range of A, then A and B can talk. And similarly, B's communication range is defined that A is lying inside it. Then only A and B can talk, otherwise they cannot talk. So which means that they are restricted by a distance D, which is nothing but your communication distance, or generally we call it R, the radius, because it is not diameter, it is radius. So if you are in the communication range of each other, then you can hear each other. Otherwise, you cannot. So now, this is true in case of homogeneous devices. If it is a heterogeneous device, there is no guarantee that B can hear A, but A cannot hear B. Right? If the communication range of A is this much and B is only this much, B can hear A, but A cannot hear B. Right? So the communication radius plays an important role, and generally we design such a way that there are two parameters in any IoT device or drones or anything. Specifically, they are trying to do sensing also. So there is a sensing radius and a communication radius. There are two important things which you have to keep in mind. The purpose of the drone is to sense around and then communicate to the destination. So there are two radius involved in it, and the radius have to be kept in your mind very carefully. They are not common R, they are called RS and RC. Right? So when you have such type of parameters RS and RC, then usually what we try to do is we try to design such a way that your RC is 2 RS in case of homogeneous devices. Right? In case of homogeneous devices, we see that the sensing radius, the communication radius is twice of the sensing radius, so that you can see that the drones are having right, and it cannot be greater than that, it can be less than that. Right? So when you are trying to do that, you can see that you are trying to cover the complete area of sensing and communication. Right? You can do the complete sensing part and the communication part, and that those are the boundary conditions we call it as. Okay? So whenever we are trying to do, we have to keep in mind that there is two separate radius, they are not same. One is for sensing, one is for communication. And if it is homogeneous, then RC, you can write it as 2RS. Okay? And if it is heterogeneous, that equation will not work. Right? So now, when we talk about ad hoc networks, you need some properties to be defined, like there should be peer-to-peer communication. Peer-to-peer means when this drone want to talk, this has to give equal option, like, okay, it has to hear, and when this talks, this has to hear. It cannot say that you are subordinate of me, I will not talk to you. Right? So we define that whenever you want to form ad hoc network, these systems are supposed to be peer-to-peer, same level. Both have to have same common functionalities. Okay? That is one important thing. The second thing is they should help us. For example, you try to see if this node want to talk to this node, there is no direct link. Right? So this other drone should help them in communicating to each other. Okay? That is another property. When these two have no direct links, there should be another drone which should help them in communicating it. You can call them as relays or multi-hop or whatever it is. They should do that job. Okay? And most properly, we call it as multi-hop communication. They hop from here to here and here to here. Right? And the third one is we don't keep drones constantly in the air in one location. They are moving around. Okay. Because at this instant, you might be looking like that. In next moment, there might be some other shape and so on. Right? Then when we are trying to develop some routines and all, there should be zero interference from somebody else. They should act on their own. Right? When we are trying to, we have developed some good procedure and we are given them, they should be able to talk to each other instead of looking at Sai Prakash, you tell me what next. I hope it is clear. You are designing some procedure or an algorithm which when you load it up, they should talk among themselves instead of looking back and asking for each and every instruction. Okay, that is what we call it a zero administration. When you load it, it has to do it. And since they are objects in the air, we cannot go there and charge them once the batteries are over, right? So you design the algorithm such that they don't drain the batteries. And the lifetime of the device should expand. It should not, like once you load it, it should live for 1 or 2 days, not for 1 hour, half an hour, and so on, right? So what we do is we design some algorithm with a low power consumption. Instead of writing 10,000 lines, you write 100 lines so that it can be executed at smaller power and it can be helped, right? So when we are trying to look for some algorithms or some procedures, what we want to impose on it, it should have low power consumption, right? So please keep in it like minimum instruction set, it should do the job. And they are autonomous. They are not depending on other drones to function. Okay? And auto-configurable. Suppose something happened in the between, they should automatically configure among themselves. They should not wait, or I have lost something, so I should wait, or I should fall, or something like that. They should be auto-configurable. Suppose there is small spike in the power supply and it has reset, it should automatically configure itself and come up, like Windows. Right? Once you close it and open it, automatically it configures on it and comes up. So you should have such type of feasibilities built into the system so that they can act on their own when they are flying and they have some problem, they try to reconfigure themselves and start working on it. Okay, we should come up with some such type of algorithms which can sit directly on the drone and try to go ahead instead of stay back or fly back, right? So we are now trying to look into something useful things to be happen. One is auto-configurable, and they should act on their own and take a decision, and they should consume less power in this process, and they have to zero administration, means they do not have to call back to the base station, find out instructions and all, and they should adapt to the dynamic changes happening around it, and they should also have a multi-hop communication and so on. Right? I think you have understood the ad hoc network, importance of ad hoc network. Yeah, any question? Yeah. Yes. Yes, it's a good question. Like, the problem over here is, let me put it in a small, simpler example. I have a class, and then there'll be 100 students sitting in the class, and I can still see some of the boys murmuring inside, and not only boys, girls also start talking among themselves, and started throwing papers on me and chalk on me and so on. So it doesn't mean that the drones are scared of it, because what we try to do is when signals are coming, multiple signals, we try to have a good terminology, the filtering. Right? If we do signal processing and all, we have a good concept of filter. So we use some type of circuitry, like even if you look into your mobile, when you're traveling on train, right? When you speak, we remove the train signals and the speak on the other side, it'll be clean, right? So we use some type of auto correlators and some filters to remove all the unwanted signals. We don't allow it into the signal. But there is a good example of a question from him, like if you have the same type of signal coming from somewhere else, right? We call it as interference, right? In case of interference, we have to deal it with very carefully, because the signal frequency is same, and it is coming from a different node which is not supposed to send it, right? So in that case, we have to be very careful in avoiding the interference also. So now to do that, I should know whether it is a rogue signal or it is the original signal. And identifying that and taking that is very power consuming. It is not low power, right? additional circuits have to come in, and it will be increasing the cost on my drone and everything. For example, in a warfare, your drone should only process your signals, not your enemy signals, right? And they keep also jammers into it so that the signal will not transmit and all, right? So in such scenarios, we have a different types of drones. We don't use the ordinary purpose drones over there, right? We use some anti-jammer circuits and all. And they are a little bit costly and power consuming also. So generally, if you try to see the drones of such type, they are heavily, the battery will be there heavily for operating for more than 2 hours, 3 hours, so that the anti-jamming signals can be removed, and some identical signal, correlated signals also can be removed, and so on, right? And we use orthogonality over there so that your signal is protected, not the other signals. The code is known only to you, not for others, right? So we have a coded signals, not just ordinary signals over there, even though you are using the same frequency, right? So they are in the signaling part, it comes, not on the drone it comes, right? Those are all, we call it a signal processing circuitry, which will be kept specially for such type of, okay, for such type of activities. The signal processing part is more serious than communication part. Yeah, you are not happy? Yeah, okay. So now let us look at what are the procedures we have to follow for the communication part. What are the set of rules we have to look at it and design our algorithm so that we can put it into the drones. So now when we talk about procedures, the set, we call it as, we divide into 2 parts. One is, first of all, you should get an access to say something, right? I want to transmit a message. For that, I should get an access first. Once I get an access, then I should know the path through which I have to go to the destination. We call it as the routing part. The first path is access path, and the second part is routing part. Even if you try to look into the OSI model and all, we keep the access part in the second layer and the network routing part in the third layer. So first we try to see how to get an access into the network, and then we can find a route to the destination and send the packet through that, right? So now, as I told you in the last class, we are trying to look into the Aloha and CSMA techniques. These two are random methodologies to get an access. We don't use a channelization or some tokenization in passing on these access, because the users, we don't know who want to talk to whom and so on. So we always look into a random access protocols rather than channelization or some master-slave communication and all, right? So when we are trying to look at it, the first one is you get a Aloha system. So when a drone has information to transmit, it just transmits. It is not bothered about the other drones are transmitting or not. So in that case, if you can see that the A is one of the drone, B is one of the drone, C is one of the drone, D is one of the drone. So A has a packet, it transmits. B has a packet, it transmits. This is the time axis. As and when C has, C transmits. D has, D transmits. So the packets, if you draw a line at the time instant, if no packet is there, only one is there, it goes safely. There is no collision. And if it is more than one is there, then collision happens. And it doesn't mean that the packets have to be in line, even if the packet beginning and the end bit, if they touches each other, then also they have collided, right? Even one bit over here and one bit over here has touched each other, it is collided. We call it as collision. And the packet is not transmitted. Okay, information is lost. So you can see that when you draw a line over here, none of the packet has started, so this will go safely. So the white ones are safe ones, and the dark ones are collided ones. So we have to see how to give access to A, B, C, D, so that these number of packets can be reduced, right? And this algorithm, if you try to see, you need 2 frame distances to avoid collision. Okay? If a packet size is known to you, you need minimum of 2 packet size free so that you can transmit it. Right? You are avoiding any overlap. Okay? And hence you can see the throughput is very small. The throughput is only given by G into e to the power minus 2G, and this is like 18% only. So to improve that, what people have done is you try to go to a slotted aloha system. You divide the time into slots, and at the beginning of the slot, there might be one user who is transmitting it. Here again, one user, he might be transmitting. Here there are 3 users, they have transmitted and they have collided. And at this instant, only one is there, he has transmitted. And here again, 3 are there, they have collided. Right? So at the beginning of the slot, only one user should be there to see that the packet goes without any collisions. Right? And by doing this slot method, you can see the throughput has increased to 0.36 or 36% from 18% to 12, because the throughput is given by G into e to the power minus G, and G for 1 you will get this access, and G for 0.2 you get this one. 2 is there, so half of that is you get it as 18%. At 0.5 you can see it has gone to 18%. At 1 G is equal to 1 you can see it has gone to 36%. Right? And most of the cases you will see that this type of algorithm has been used. It is still being used. It is not that because the throughput is very small, people are not using it. It is not the case. You can see that low data rate tactical satellite communication networks, people are using it because the number of stations are very small, and hence they can increase the throughput. Right? As n increases, the load is decreasing. If n is going down to 1 or 2 are trying to communicate, they are success only. Right? So even the subscriber-based satellite communication network or mobile telephone call setup, they are still using that to find out where the mobile is and so on. Okay, set-top boxes communication or RFID technologies. These are the places where still slotted aloha is used, where the number of users are very small. Right? If the number of users are trying to increase, then the throughput of this system will go down. So you can see as the load is increasing, the efficiency is coming down. Right? So I think so far it is good. Okay, so let us move on to the next one. So the modifications of that, the aloha system or slotted aloha systems, people have tried to improve the efficiency of that by doing a reservation type of aloha. So what we basically try to do is, at this point, if there are more than 2 or 3, why can't we do some type of reservation system? Whoever comes first, I'll allow, others I will not allow. Right? See, at this beginning of the slot, there are 3 people, like booking counter in a theater. Open the gate, all the people will come. First person I'll give first ticket, second person I'll give second ticket, and so on. So that I am reducing the fighting between the people. Right? I'll put a bar, and whoever enters first will get the first ticket. So I can still improve the collisions over there. Right? I can see that the collisions are trying to decrease, and we modify this algorithm and call it as a reservation aloha systems. Okay, and if you want, you can search into this lanetworks.com. They have given you the analysis of that, and they also claim that the efficiencies are increasing up to 60, 70, 80, depending on the load and so on. Okay, but it makes some meaning on it. Like what we are doing, we are not allowing everybody to transmit. We are allowing only the first person who is standing on the line by that. So how we do that? On the air, you have to do it. You will not put a counter over there and ask them to come in and all. So how we do that? It's a simple example. I think you might have studied that we have a backup algorithms, right? It can be a binary backup. It can be any backup algorithm. You can use it. So what we basically try to do is, when the users are coming here, I will give them one number. Okay, first person 0.8, second person 0.66, another person 0.2, and so on. It is like a counter. You have 6 number, he has 4, he has 2. So you start decrementing your counter. And whoever come first will transmit, others will be seeing that some transmission is going on, so he has to come at next lot, right? So we have different ways of doing it, okay? So that is one method you can think of reservation allocation. And there is another methods also, demand access or packet reservation multiple access. This is what we call it as contention window. We open up a contention window, and during that, whoever enters will get priority of transmission. I think, have you anytime seen the reservation counter of Tirupati and all? There is a counter which will be open, and you will be in the counter counting down 1, 2, 3, 4, and once your turn comes, then you can enter, right? So anybody who wants to transmit will have a counter open, and they'll be given a chance after some time, and then they can transmit. That is one way of looking into things. Okay, so demand access, you can, as the demand increase, your counter number will increase, right? I think people might have experienced that. Some will get 2, some will get 3, some will get 7, some will get 4, and so on, depending on the token when you have, right? So these are some of the modifications what people have done when the network size is very small. As the size goes on, these type of things comes up. Okay, you have to resolve something before a collision happens. And that, how you do it, it is up to you. You can take a pack of cards of 10, give it 1, 1, 1. Whoever gets 1 will come, 2 will come later on, 3 will come on later on, and so on. Right? It is like a dice. You throw it. If it is 5, you take 5. Another dice, you throw it 4, 4, and so on. So we have number of mathematics in that, right? And this is one paper where they have written about this PRMA and DAMA and all. You can have a look into it if you want more details about it. So now these are the potential candidates who are trying to play on the drone networks to see whether the access is obtainable or not. How fast you can get an access onto them, because in the drone network you cannot wait for a few hours to get an access, right? We need a faster access, and as the number trying to increase, right? For example, you are the drone over there, Swiggy delivery drone is there. It is trying to travel to your destination, the person who has booked it, and in between there is some other drone, Amazon has came and it is trying to deliver at the same person. Then these two cannot clash each other, right? So there should be some mechanism so that they can access at a faster rate and try to take another round turn and then come back, because they cannot stop over there, they might fall down. So what they do, they change the trajectory, go around for some time and then come back by the time this will go away, right? So there are some mechanisms which we try to play to see that the collisions are avoided between the drones also. So now coming to routing, I given you some picture on, and before that we have, I have not kept it, we have carrier sense multiple access. This is another important technique what we try to use in routing. So what we try to do is we try to sense the media and see whether there is some communication going on. So the drone will sense the media and try to see whether any communication is going on, and if something is going on, he'll keep quiet, otherwise he start sending it, right? We call it as carrier sense multiple access. And I told you yesterday, the carrier sense multiple access is not that simple, because we might land up in exposed terminal and hidden terminal problem, right? When I am trying to transmit to some X in my communication range, I assume that there is no other drone on the other side, right? That is hidden terminal problem. There is another drone on the other side which is trying to do the communication and which I am not able to assess it. Say, for example, there is a drone B and a drone A, and A and B want to communicate, but there is one more drone C which is trying to communicate to B. A doesn't know that C exists, because A communication range is only up to B. And C communication range is only up to B, it doesn't know A exists. Okay? So A doesn't know that C exists, C doesn't know that A exists. So they start communicating it, and at B there is a collision. Right? None of them will be able to transmit because this has sense that there is no communication, it starts. This has sense that there is no communication, it starts. And both try to crash. So this is what we call it as hidden terminal problem. And similarly, we have an exposed terminal problem. So these two has to be handled before we start the communication, right? And so for handling that, we have what is called as RTS and CTS communication. Request to send and clear to send. So when you have stations B, A, and C, when A want to communicate, it only sends RTS. And assume that when you have a message to be transmitted, your RTS size will be only this much, right? The probability of collision of RTS and CTS is very small because the size of the packet is very small, right? So we assume that the RTS CTS packets will not collide. They might collide. It is not that there is no chance. They might collide, but the probability of collision is very small, right? It might be 0.001. Okay? And this will happen in case of homogeneous network with equal distance between the drones, right? If the distance between A and B and C are constant, right? If A and B and C are constant, and if both are started at the same instant of time, then there is a collision. And happening that it will be very difficult, right? So we don't assume that the equidistances will be maintained between the drones. Okay, and hence collision of RTS and CTS probability is very less. Right? In that scenario, RTS and CTS will help us to reduce the number of collisions on the network. When we send RTS, A sends an RTS, B sends a CTS, which will be heard by both B and C. Right? C propagates. It is not that link. It propagates. It goes around, right, in a circular fashion. So C and A can hear it. So when C hears CTS, it is not supposed to transmit until the end of data transmission, right? So after CTS, it starts the packet transmission, data packet 1, data packet 2, and so on until the end of transmission, EOT. And once it hears EOT B, it sends terminate, right? On hearing terminate, C can start transmission. I hope it is clear, right? When you have ABC, when you have ABC and you are trying to transmit it, you have a RTS signal transmitted, and B will say, okay, clear to send, and that will be overheard by B and C. And then you can see that once CTS is there with C, it will not speak anything until it gets EOT signal, right? And once it gets EOT signal, then C is ready to transmit it. Okay? And this is mostly done in wireless networks, in hidden terminal problem. Exposed terminal problem, a D is here, and RTS has came here. Because A has sent RTS, so B and D has heard it. And it will see whether the packet is meant for it or not, right? And this RTS will have B, so D will not speak, right? Okay, so it says RTS A, CTS A, so this will not speak, and this will not speak until again EOT comes back, right? So now we call it as a vector where you have first value is RTSB, second value is data packets and so on, and then CTS. So those things have completed, then they can release it. And the other stations can start talking. So if you try to look into the drone networks, mostly they have to do this RTS, CTS. And here, luckily, I have drawn the one-hop networks. So it is a mesh network. So everybody can know what is CTS, what is RTS and CTS. So if this station sends RTS, these two stations knows that there is a communication. And if it is meant for this, the other one will keep quiet and the communication goes on. And once it sends end of transmission, this can start transmitting. So that's how the links will be activated and deactivated. And now, mostly what we try to look in from here is, when you think about a message packet, right? When we think of message, what is message packet? I want to send some information. The information what these devices can understand is zeros and ones only. They don't know natural language processing. They don't know Telugu or Hindi or Tamil or Urdu. They don't know anything. They only zeros and ones they know. So your message, voice or whatever it is, we are converting into a digital format. So it is nothing but zeros and ones. Some set of zeros and ones, right? And this packet, the message, has to be delivered properly at the other side. So the machines which are hearing that should know where exactly the zeros and one it has to start and where it has to end, right? So we say that, okay, beginning of it, we put some information called as start of packet, and at the end, we put stop of packet, right? We'll keep a start of packet and end of packet so that the other drone knows that it has to read from here to here. Okay? So this is what we call it as header and trailer. So now the another question is, if this header is nothing but a sequence, right? So generally we keep 0 with 6 ones and a 0. At the end also we keep 0 with 6 ones and a 0, right? So whenever you get this sequence, you say you start reading from here. And whenever you get this sequence, stop reading from there, right? So when you are trying to look at this, suppose this type of sequence comes in between here. It terminates over there and says your packet is ended. But that's not our intention. This is the actual end of thing. But such type of sequence have came here in your data and it is terminating. So what we do is we do bit stuffing to see that this type of information is not available here, right? We do bit stuffing to see that this type of frame is not existing anywhere here. And at the other side, after receiving it, you remove that bit and take it. Okay? So now, by doing this, what is that we are getting out of it? The other station to whom you have addressed it is not there. You are sending a message packet. You kept it, your letter in an envelope and you have sent it, but you have not kept the address on top of it. Okay, you cannot do that, right? You have written a letter, the message, and you have taken care that there is an envelope with this side and that side. You kept it in an envelope, sealed it, and now you have to add address to it, right? So we have to, there are two ways of doing it. Suppose I want to send a letter to him, right? I have wrote a letter envelope and I have already decided that I send him via this path. I'll call my Venkateshwar and ask deliver to him. So there is no need for address for it, right? There is no need for address because he has been identified and the carrier knows that it has to be given to it and he takes the letter from me and he will give it to you. Which means that I have to establish a path first between the source and destination and send the messages first. So there is no confusion at all, right? I established a path and whatever it sends, it goes only in that path to the destination. So you don't need an address in that case. right? And if I have not decided the path, I have to send it somehow, I want to push it, then I need an address. The destination address I have to keep it. And when I keep destination address, so there might be a person like me who is not bothered, I don't know who is he, and throw it. Right? So there should be a source address also informed saying that this is director of NIT, you have to read it. Right? So a source address is also required over there in case the route is not finalized. So now we have two options. One is connection-oriented protocol, and the second one is connectionless protocol. So please remember that in a connection-oriented protocol, the overhead, what is required, is very less, and a connectionless protocol, the overhead builds up. Right? You have to give complete information of everything what it has to do. I think you are in line, right? When we have a connection-oriented protocol, the overheads can be reduced, and in case of connectionless protocols, we have to put a lot of information to transmit it. So now, if this message size is very small, 1 KB or less than that, and this is taking around 2 KB, then what I am supposed to do? Because the data what I'm sending is very small, but the address part is very big, right? So in that case, the efficiency throughput on the network is very less, but it is essential that without this cannot travel, right? Without this cannot travel, and hence we need it, okay? So you cannot fight on some things in some cases, especially in drone technology and all, wireless or UAVs. And if you look into the terminologies, the unmanned, you try to drop that unmanned vehicles, aerial vehicles and all, because there is no unmanned, uncrewed. There is no crew on the board. There is a man who is controlling it, right? So don't say unmanned. There is no crew on the vehicle. There is no crew on the vehicle, so it is called uncrewed autonomous vehicles, right? So there was a lot of discussion on that, because actually it has started as unmanned because nobody is there sitting and controlling it, but there is a person who is controlling from below, right? So please remember that whether the routing protocols what we are trying to look at can be categorized into two groups. One is connection oriented, the other one is connectionless. So now coming to our drone technology and wireless network, even though the connection has been established, right? The connection establishment will take some time. I think you might know that when you call your friend, you dial a number and you wait until the connection is established. Then you start talking on it. So there is a finite time involved in establishing a call. And if this time is increasing, what does it mean? There is the load on the network is trying to increase. It is not able to find a free path for you from source to destination, right? So now as the drone network is trying to increase, because today it might be 1 or 2 or 3, but in the future, if you try to see, there may be thousands of drones which are flying. In that case, establishing a connectivity itself is a very big Hercules task, right? And we have to spend sufficient amount of time in finding a path. So really good, you have made a good effort, you find the path, and now there is some rain or something happened and the link failed. And you have started transmitting the packet, right? So it's not only establishing the path, maintaining the path comes into the picture, which is not there in case of wired network, right? You don't expect a wire to break within a half a second, right? And it will not break because there is a metal inside and protection outside and everything is there, it will not break so easily until something willfully you cut, right? So in wireless network, it's not like that. The links might come up and go down also because of the environment. Or there might be some obstacle came here and there is a link failure, right? There is some bird or something else flying and the link failed. Okay, so when such type of thing, when you have struggled hard to establish a connectivity. And after everything is good, I want to send data, the link failed. Right? So now how to handle that? We have to see that the route is being maintained to instantly know that there is a link failure. And if you know that, you have to tell the network that there is a link failure. Right? We have to tell the network that there is a link failure, and the source have to start searching for an alternative route. Right? So we have very difficult tasks in wireless networks compared to wired networks, and those things have to be addressed very carefully. So for doing that, we have two types of routing protocols been proposed. One is proactive, other is reactive. So reactive, I'll try to spend, because proactive is a little bit towards the static nodes, not towards the dynamic nodes. Right? Static means assuming that, okay, the links are, the network is stationary, like geostationary orbit. Their round is in the orbit, and we know that they will not fail for some time. Right? For that, we can think of some other network. But for the drones coming up and going down, it is something like a dynamic in nature, and it is not, you cannot approximate even for a few seconds as a static network. So in that network, reactive types will play an important role. So if you try to look from the reactive point of view, or basically let me explain you these three methods before we go into the flat routing. So we have three types of ad hoc routings which are available to us. So I have multiple drones flying around, and I am only concerned about the corner 4 drones because there is something which is going to happen over there. Because the weather station told that there will be some rain in the corner, so I have to concentrate on that. I have to make some arrangement for that. So we call it as geographically you're trying to find some location and trying to do some activity over there. I know that the drones are flying in some portion of the network where the corner has some problem over there, I have to look into it. Or I have to send some message to the corner, then also geographically. So for geographical routings, mostly they are based on GPS. And please remember that GPS is, how many of you use GPS on your mobile? Most of you, right? And how many times you charge in a day your mobile? Once. So if you don't put off your GPS, how many days you will charge it? 4 days, right? So you can see the energy, how much it is consumed by a device if you keep your GPS on, right? So when you are trying to look from the application point of view, there are some few drones which are like low battery operated view, right? There might be 9 volts battery which is used for driving the drones, and there might be a 20 volts battery which should be used, and there might be a car battery like that which can be used for, but the weight, if you try to look at, they are very heavy. And to lift that, you need a much bigger drones, right? So there is a compact factor for a drone which tells you how much battery, how long it can live. And now your routing algorithm should help it rather than overload it, right? So if you are trying to use a smaller one, GPS is not at all a solution. It only tells you where exactly it is, but without GPS also you can find out the locations exactly where it is, right? Because you have a good, if you are good in mathematics, you have triangulations. Have you heard about it? Triangulations. You can easily find a location of it. So each drone, you can think it as a, if there are 3 drones which are having A and B and C have GPS, D doesn't need it because they can use some triangulation method to find out the location of D, right? So you need only a fewer number of drones which can carry GPS. The other drones can easily find out their location with respect to A, B, C. And they can use that for the monitoring purpose. So don't always think that every drone should have GPS. And there is a form factor, as I told you, if the drone has a larger capacities and all, you can think of GPS. If they are very small, right, if they are very small, you don't think of something like GPS luxury on top of it, which consumes a lot of. And in such cases, the geographical routing will help us. If you know that you have to travel towards east, you go only towards the east. Don't go to north, south, and other locations. Okay, so that is what we call it a geographic routing. And the other one is hierarchy. As the number of drones are increasing, we don't try to communicate from all the drones. We see that to save energy, we form the drones into clusters, and we take the cluster heads only, we try to communicate. Okay, so we are trying to put it something like there is a cluster head A, and so there might be a cluster of drones. So they form into a cluster, and they communicate only to A, and A will try to communicate to another cluster head. And this will be communicating to these two, will be trying to communicate. Okay, only the cluster heads will try to communicate, which has more energy, and the small energy device only try to communicate to the cluster head. So this is what we call it as hierarchical type of routing, but this will be used only in case of large drones, and they are doing the same job, right? Then we elect a cluster head and ask them to, like what we try to do over here, like we separate the students into departments. If you have problem, talk to your head of the department. All the heads will talk to director and so on. There is a structure over there. So we try to do that to minimize the energy consumptions in the network. Okay. So the otherwise, we always go for a flat routing, and we have proactive and reactive type of communication. So any questions related to this? So if you try to look from the comparison of reactive and proactive, generally we have to do it in two terms. One is latency and other is overhead. These two plays an important role. And we have to trade off between these two, keeping in mind that mobility is there in the network. If the nodes are trying to move, then we have to think about either latency and overhead. One of the algorithm will give you latency, one of the algorithm will give you overhead. So you cannot say that this is good and that is bad. Depending on your mobility patterns, you have to take a call which one you want it. Any question? No. So in this case, what we'll try to do is, before we start the routing protocols, we'll assume that all the nodes in the network are participating in moving the packets, forwarding the packets, right? So if a packet comes from A to B, B will forward it, let us assume C, D, E, F and all, and they will be forwarding it and so on. They are spreading the message. It's like a flooding. If I send a message, you try to spread it out. Good example is gossiping, right? I think you heard about the word gossiping, right? If I give a message, they start spreading like gossip among your friends, and they will try to spread it out and goes to the end. And the problem over here is in gossiping, the message M will become message N at the end. But here we are not expecting something like that, right? Okay, so the flooding is a mechanism where we spread the message to all the nodes in the network. So we are not assuming that the diameter of the network is very large, right? We assume that it is a manageable network, which is not running into 10,000 nodes, 1 million nodes, and so on. We are assuming that reasonably a small size, okay? And why we are trying to do that is, the number of hops we are trying to put it as some n hop or something. We don't take it a infinite number of hops and so on, right? And and if this is too large, then the overhead tries to increase. Okay, the overhead also tries to increase because the number of hops has to be included in your packet. So start this one, next go here, next go there, next go there, go to the destination. So we'll assume that it is not too large, so that the packet header is also limited to some reasonably good amount. And we also assume that the nodes are not running very fast, they are moving very moderately slow. Okay, because if you try to see the speed of drone and all, they might be catching up to 100 kilometer per hour, some are 50, 60, 70, 80, and we will not assume that it is like a bullet train 600 kilometers not running, right? Moderate speeds are there. Because why we are taking it in our theory is because once it becomes disconnected node, we will not be able to communicate. So we are always assuming that they are within the limits and we can easily communicate with them. And when we are trying to discover the routes, we assume that the information what the middle node has will keep it for finding the route in the next case. Suppose I know that the route is A to B, B to C, there is a link. So B need not have to search for C, it is already there in the path, right? When A has sent a packet, B has sent to C, B knows that A is on this side and C is on this side. B need not have to discover again A and C. So that is what we call it as cache. Okay? So the local route cache will help us in finding out the routes very faster. And assuming that the topology is still same, the links are still active. If the links or the topology changes, then the cache is no more used for us. Okay? And all the nodes are hearing. It is not that some nodes are sleeping and some are hearing. We assume that all the nodes are hearing, because why we have used this case is, you can see that in most of the sensor networks, we make them to sleep. Okay, in the sensor network, we make the nodes to sleep, don't drain the energy so that the life of the network can be extended. But in the case of drones, we cannot ask them to sleep, right? They have to be running only. Okay, so please remember that this is one important thing which makes the earlier ad hoc sensor networks routing to come up with overhearing. We assume that always the nodes are active, waiting for some message, either to be relayed or to itself, right? And we have not used any energy saving in our assumption, assuming that all are equally powered and all have power to fly from source to destination, right? So we are assuming that all nodes have working and we are not applying any energy savings on the algorithms. Sorry? We are assuming that, because we are not taking up that drones are sleeping and the drones are kept in energy saving mode and all. Because, yeah, continuously. Yeah, because see, generally what happens is when we are coming for the drones as well, that's what I told you. Sensor networks have a different architecture and the drones have different. Sensor networks, we assume that energy is criteria, we make them to sleep, okay, and we save energy. So generally what we say is the life expectancy of a sensor network is 10 years. For example, you have thrown the drones on the border area of Indo and Pakistan. So you don't go every morning and charge them, right? We leave them assuming that 10 years it works. So, and we make them to sleep and we wake them up when it is required. But we cannot apply the same technique over here. We cannot ask drones to sleep and wake up, right? They have to be wake up when they are in move. If they are sitting here sleeping on the table, it is fine, they can sleep. But when they are working, they have to work. That's the meaning of overhearing. So when you take a drone network, right, we are not putting it into a structured format, it is an unstructured format. Because in a structured format, the things are much easier because it is a linear networks. Or some structure is there, you can say they can talk vertically 3 drones like this and 3 drones in a horizontal way, or some angle we can define it, whereas in an unstructured network we cannot define it. You have drones flying, and they can talk to each other on their, if the link exists. If the link doesn't exist, they don't talk. For example, there is no link over here. The two are isolated, whereas the other networks are connected together. And you can still see that these two cannot talk. Okay, so there are drones which can talk to each other, and there are drones which are isolated. There are drones which are directly connected. Some drones are indirectly connected, and we have a large structure of networks. So in this case, if assume that D wants to connect to L, D wants to send a message to L, right? Because we are not sure whether what it is, but D wants to send a message to L saying that I am coming behind you, because let us assume that this is Swiggy drone and this is Swiggy drone. Rest of the drones are somebody else. So it is saying that it wants to communicate to L whether you have delivered, coming back, or I can start from here. So some message it is right. So now when we have such type of network and we want to route the message from the D to L, okay, and we are assuming that all other nodes are helping us, which are there in the connectivity. Right? So in such type of network, we have to find a route from D to L. Okay, our task is to find a route from D to L, and it should be generally what we teach is shortest path. Right? In most of the networks, what we teach is find a shortest path and go. For example, if you want to go from here to Hyderabad, what is the shortest way to go? Right? Some people have time, some will think about distance, some will think about the money, and so on. Right? For some people, money, they see what is the cheapest path we can go. Some people, time, they say what is the fastest path we can go. Right? So there are different cost parameters. I am not discussing on cost parameter. We'll assume that only one is there. I have to find a route from source to destination, and that should be the fastest way. Right? I have to find a path, and now let us assume that I have 10 packets. I have sent only 5 packets, so 5 packets might go like this, and the another 5 might go like this. At that instant, that is the shortest, so I sent 5, and after that, the network topology has changed. I found out again, and I found this is the shortest path. So there is no guarantee that all the packets will travel on the same route. Whichever route is there existing, I'll send it, and if the link fails, I'll find another route and send it, and if the link fails, I'll find another route and send it. Right? So I can find different routes in the same transmissions also. Okay? So the problem here is very clear. We are supposed to find a path between source and destination, and the procedure should be the fastest way, because I cannot wait for one day for finding the path. Instantly, as and when I want it, I'll send it. Right? And the path, if the links are failing, the alternative path should be existing so that I can transmit the packet through that. Okay? So in that scenario, we'll try to see how to start with it. Right? So now we have 2 basic route discovery commands. Right? We have 2 commands. So whenever a station wants to transmit, we send a request packet. Right? We use one command called as request packet, route request packet. So A want to transmit, it generates a route request packet and broadcast it. Broadcast means, in a wireless network, broadcast means whoever in the neighbor can hear it. Right? Broadcast means it airs it, and whoever is there in the communication can receive that. And the neighbor has to transmit it again. Okay, it is like a relay node. When it hears some request coming from someone, it again airs it. Again, whoever is there in the communication range will hear that one, and he airs it again until the destination hears it. Okay, the procedure is clear. Like when A want to transmit, it just airs that one. So whoever there in the communication radius will hear that one, and the neighbor will start airing it. Again, the neighbors can hear that one. It can air it until it reaches to the destination. Right? And the destination node, as and when it hears it, it says, okay, reply back. I heard about you. You can send me the package. So again, it comes back to A. So A knows that, okay, there is a destination. It can hear me. It has sent a message. I can hear it. So I can send it back. Right? So now the problem is when I say reactive type of communication, right? So as and when I have a packet, I try to discover the route. It is not that there is a frozen routes from which I'll pick it up and do. Right? In most of your routing algorithms, we discover the tables and keep them. Whenever we have a packet, we use that table to transmit it. But here we are not doing that. Right? We are trying to generate the route as and when I have a packet to transmit. Otherwise, I will not discover. Right? I think there is slight difference. As and when I have a packet, I try to discover the route and transmit the packet. And I am not storing that information. Okay. So now, so this is fine. We have a request and a reply. Like what I told RTS, CTS, it goes. Then if the link fails, there is a error message which tells that there is a failure over there. Okay. So these are the basic mechanism used in most of the routing algorithms when we are trying to communicate to drones on the network. Okay. So now when I air the packet, all the neighbors will hear it and they will start airing it. So you'll see the load on the network. These packet load on the network, you can see it. So I have to somehow remove all those unnecessary packets from the network as fast as possible so that there can be other communication going on, right? So I have to see over here the data packets and you collect the route and see that all these junk messages have to be cleared as fast as possible so that the message can be transmitted. Because when I transmit the message, somebody in the middle should not hear that the A wants it to transmit to D, right? And these two will collide. Okay, so there should be some way that old junk has to be removed as fast as possible so that the new packet can flow into the network, right? So there should be some way of trying to maintain the network so that the packets can flow into the scheme. So now, so when D wants to transmit it, it transmits the packet saying that I am D and I want to go to L. The packet is generated to D, but it is meant for L. So actually L should be there also, but it is implied that D want to talk to L, right? Because all the packets will have L, but I am not interested in L. I want to see how the route is discovered. So you have D written on the packet and it is transmitted. So you can see that in the first instance, D has broadcasted, all the people who are in the neighborhood can hear it. The links are black has become red, right? In the earlier case, if you try to see, sorry, they are black. There are 3 links which are black, and now those 3 will become red. And the next step, these are the neighborhoods which has to broadcast. So you can see the next one, they have transmitted saying that the packet came from D and B, it came here. So DB packet has came here. And similarly here, D and G packet came here, right? So whenever a packet is passing through, they will put a stamp and then transmit it, like your postal department. Whenever it goes, they put a stamp and send it, again put a stamp and send it. So you know the route over there. So we also do the same thing, put a stamp and send it. And in the next hop, you can see that they are going increasing to the next level, and then finally you have 2 routes coming to L, right? One is from the above and one is from somewhere below. There are 2 routes came to. So now L has to decide which route it has to go. So now, any problem? No. So now let us assume physically what it happens. When L receives 2 packets simultaneously, there is a collision, right? There should be a collision. It will not receive both saying that I have received both. So there is a possibility that one packet, one of these, have reached faster than the other, right? There is a possibility that one of the packet might have reached faster than the other, because both cannot receive at the same time, because both collide and both are lost. If a packet has been received at L, one might be first and next one is the next instant. So whichever is first, whether this one or this one is first, it replies back with that name, with that tag, so that the A knows which route it has to follow. Right? I think the example is clear. L, whichever L receives first, the packet receives first, it uses that path to tell D, use that path to transmit. Right? So D, when it sends the message, it puts this path and message and transmit it. So the packet is marked with D. It has to go to G, it has to go to J, it has to go to K, it has to go to L finally and reach it. And if the hops are more, this will try to increase and the overhead tries to increase. Right? If the number of hops are increasing, this will increase. Right? Overhead, multi-hops will increase. And the overhead is trying to increase. Okay, that's the only disadvantage with this dynamic source routing algorithm. Otherwise, we can happily use it on our, right? So we are trying to flood the network with the route request packet and trying to get back the reply from the destination, which route we have to transmit, and we transmit the message using that only. And L will send back the reply in that route only. Right? So most of the cases in the drones and all, we try to use this type of algorithm to reach it faster. So I think I'll stop over here. It is almost 5:30. And if you have any questions, I can answer them. No problem, man. I will not take it something serious. Forget about hops. Now there is no question of hops. Whichever packet L reaches fast, after 10 hops also it reaches fast, it uses that path only, because the time delays are more important for us in the drone communication. It is not hop count, or it is not the length by scale and all these things. Okay, I want to deliver the packet immediately to L. So whichever is the smallest path, because L has told that it has received this reply first. So that is the shortest. But both will not reach the same L at the same instant, because there is a collision happens if both come set at the same time. So one will come before the other. So yeah, the time difference might be few fraction of a second, but whichever reaches first is the path. Right? So that's why I told him, like, energy is no constraint, path lengths are no constraint, number of hops no constraint. L, whatever it is received first, will be the path I pick up and send the message. Yeah. Yeah. No. See. This will help me in caching the route. So if this link fails, I can still use where is L, who has the L. I can ask who has L, and that path I can use it. That's why the caching will come up. Route maintenance will come up. Yeah. Every node knows what is before it, what is behind it. Right? See, this node knows it, like B, C, B, D is there behind him. Right? You need not have to discover again. Yeah, cache is there, it is already having that information. So if the J says that there is no route, H says that I exist. Right? So you can send it through other paths also. So in that way, we start routing, maintaining the roads. See, one transmission is helping all the nodes to know where exactly they are. And they will help us in finding the alternative to transmit it. Right? Any more questions? No. We'll stop over here. Okay. Thank you all.